Welcome to the course, Machine Learning with Hands-on Experience in Python and R, under Part 3b, such as, K-nearest neighbors, KNN, support vector machine, SVM, kernel SVM, and naive Bayes. This course is fun and exciting, but at the same time, we dive deep into machine learning. It is structured the following 10 parts to be the master machine learning on Python and R. In this video of Part 3b, we will discuss following 4 important parts of classification under Part 3b.
Hello and welcome back to the course on machine learning. In today's tutorial, we're going to talk about the K-nearest neighbors algorithm. Alright, so let's get started. So let's imagine that we have a scenario where we have 2 categories already present in our dataset. So we've identified 2 categories, and one is category 1 on the left, which is red, category 2 is green on the right. And for simplicity's sake, we're just going to take into consideration 2 variables or 2 columns in our dataset. So all of this grouping is happening based on these 2 columns, x1 and x2. And now let's say we add a new data point into our dataset. The question is, should it fall into the red category or should it fall into the green category? How do we decide that? So how do we classify this new data point? Do we classify it as a red data point or a green data point? And that's where the K-nearest neighbors algorithm will come to assist us. At the end of performing this algorithm, we'll be able to identify whether it's a red or green point, and in this case, the point turned out to be red. So how does the K-nearest neighbor algorithm work? How did it do that? Well, we're going to build a step-by-step rule guide to the KNN, and after we've built it, we're going to actually perform it manually to see how it works. And as you'll see, it's a very, very simple algorithm. Alright, so the first step is to choose the number K of neighbors that you're going to have in your algorithm. So you have to identify whether K is equal to 1, to 2, 3, 5, or some other number. And one of the most common default values for K is 5. Next, you need to take the K nearest neighbors of the new data point according to their Euclidean distance. Now here, you don't have to use Euclidean distance. You can use other distances such as a Manhattan distance or any other distances that you might be considering. But in most cases, the Euclidean distances are used, so we're going to stick to those. So once you've taken the nearest neighbors, among these K neighbors, you need to count the number of data points in each category. So how many data points fell into one category, into the other category, and so on. If you might even have more than 2 categories in your data set, so you just need to calculate how many fall into which category. And then you need to assign the new data point to the category where you counted the most neighbors. As simple as that. That's why it's called K-nearest neighbors, and then your model is ready. As you can see, it's a very simple algorithm, and moreover, we're just going to do a manual exercise right now to really solidify this knowledge. So let's move on to that. So here we've got the new data point has been added to our scatter plot as we saw previously. How do we find the nearest neighbors of this new data point? Well, let's have a look at the Euclidean distance that we're going to use. So Euclidean distance is a very basic type of distance that we define in geometry. It's the one we use in geometry, and basically if you have 2 points over here, P1 and P2, then the distance between the 2 points is measured according to this formula. So x2 minus x1, the difference between the x coordinates and then squared, plus the difference between the y coordinates squared, and then you take a square root out of all of that. And that is basically, if you look at it this way, it's a right angle triangle, and so you're taking one cathetus and you're squaring it, you're taking the other cathetus and you're squaring it, you're adding them up, you're taking the square root, and that gives you the length of the hypotenuse. So there we go, that's how Euclidean distance work. Again, you can choose any type of distance, but this is the geometrical distance, and this is the one we're going to stick to. So basically on a scatter plot, a 2-dimensional scatter plot, we can just draw the lines and see what is closer. So here's our new data point. How are we going to identify which are the closest 5 neighbors? So basically we just look at them and we see the distances here. So we can see that's the closest one, that's probably the second closest one, the third closest, fourth closest, fifth closest. So let's outline those. There we go. So now all we have to do is step 3, among these K neighbors, count the number of data points in each category. You can see in category 1, in the red one, we have 3 neighbors. In category 2, we have 2 neighbors. So therefore, Step 4, assign the new data point to the category where you counted the most neighbors. That means we need to assign it to the red category. As simple as that. There we go. Now we have classified this new point and your model is ready. There we go. It's a very straightforward algorithm, one of the simplest you can think about it. So it's very good to get this section started with a simple example like that. And also we're going to have a look at some practical exercises, and Hadlin will show you around R and Python. I look forward to seeing you next time, and until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which we're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. Today we're going to implement the KNN algorithm, k nearest neighbors. So let's start with the first step, that is to set our folder as working directory. So we go to File Explorer here, then we go to Machine Learning AZ, Part 3 classification, and then k nearest neighbors here. And that's our folder we want to set as working directory. So make sure that you have the social network add CSV file, and if that's the case, you're ready to go. You just need to click on this button here, and we are all set. And now let's start to implement the KNN algorithm. So of course we're going to use our classification template that we made in the logistic regression section. I'm just going to take everything from here to here, copy, and paste it here. Alright, and now we just need to change a few things and our model will be ready in a flashlight. So the few things we need to change is actually in this section where we have to create our classifier. but it's just going to take 3 lines. You know, we need to import the library, then we need to create the object, and then we need to fit the object to our training set. So it will be very fast. Let's first pre-process the data by selecting all this and press Command or Control plus Enter to execute. Here we go. All pre-processed correctly. Now let's go to Variable Explorer to check if everything is fine. So we have our data set. As a reminder, this contains information of users in a social network. This social network has a business client, which is a car company. The car company puts ads on the social networks, and the social networks gather the information whether the user clicked and bought the product, that is the car. So it's 0 if the user didn't buy the product, and 1 if the user bought the product. So the goal here is to make a classifier that will classify the right users and put them into the right categories by predicting if each user is buying or not the SUV. So let's press OK, and we have our training set, X-train, Y-train, and our test set, X-test and Y-test. Perfect, and now let's create our classifier. Okay, so which library will we need to import? It's the scikit-learn neighbors library, and from this library we will import the k-neighbors classifier. So let's do this. From sklearn.neighbors, here it is, import k-neighbors classifier. Alright, that imports the class, and now we're going to create an object of this class. So as usual, we're going to call it classifier, okay, equals, and we're going to copy this because we are calling the class. So copy, paste it here, and then we will choose our parameter. So let's press Command I to inspect this class, and here it is. So there are the parameters. So the first parameter is n neighbors. Okay, so which number of neighbors do we want to choose in the KNN algorithm? So we're going to pick the default number, which is 5 neighbors. That will be way enough to make a good classifier. We will see in the last section of this part how we can improve the KNN classifier, but for now let's just take the default number. So here we're going to add n neighbors equals 5. Then the second parameter is weight. Here we don't care. We don't need this parameter yet. Algorithm, we don't care either. Leaf size, we don't care. But we care about metric and p. Because as Kirill explained, the KNN algorithm is based on Euclidean distance. And we want to choose actually the Euclidean distance as a distance base for our algorithm. And to choose the Euclidean distance, as you can see, we need to first pick the Minkowski metric, and then here we need to choose p equals 2, because as you can see, power parameter for the Minkowski metric. So that means that when we select the Minkowski metric, then when p equals 1, this is equivalent to using Manhattan distance, but that's not the distance we want. We want the Euclidean distance, and actually the parameter for this is p equals 2. So what we will just need to do is just add those two parameters, metric equals Minkowski, and p equals 2. So let's do this. Let's add here metric equals Minkowski and p equals 2. And that's it. The classifier will be ready with only those 3 parameters. Alright, so now that it's ready, let's fit this classifier object, because this is an object of the k-neighbors classifier class. Let's fit this object to our training set. So to do this, we do, as usual, classifier dot fit. So we use the fit method here, which is a method of the class k-neighbors classifier, and then we fit it to x train and y train. Perfect, and now it's ready. Let's select these 3 lines here, and here we go. Everything should be fine, and it is fine. Perfect. So these are all the default parameters that were selected by default because we didn't specify them, and now it's ready, so we can predict the test set results. Let's do this. ypred. Here is ypred. Now if we go to Variable Explorer, we will find ypred, which we can compare to ytest to see how it's doing. Okay, so this is ytest, this is ypred, so that means this is the truth and this is the predictions. So let's compare. Okay, from 0 to 6, the truth is 0, that is the user didn't buy, and the prediction is 0 as well. That means that our model predicted that the users going from 0 to 6 didn't buy the SUV, so that's good predictions. 7th user bought the SUV because it's a 1, and the prediction is 1 as well, great. 8th user didn't buy the SUV, 0 as well, great. 9th, 0 here, in reality the 9th user didn't buy the SUV, but our KNN classifier made a little mistake here. He predicted that the 9th user bought the SUV. But it's okay, it's normal. We will always have a few incorrect predictions because all models are wrong, but some are useful. And this one will definitely be useful, but it will not be right 100%. So let's press OK. And now let's have a look at the confusion matrix to see in one shot the number of incorrect predictions. So let's do this. We don't have to do anything here because the template is made in such a way that we don't have to change anything except for the classifier here. So let's do this. Let's press Command and Control plus Enter to execute, and here it is. The confusion matrix CM is here. Let's have a look. Wow, not bad at all. As you can see, remember in logistic regression we had 11 incorrect predictions. Now we have 4 plus 3 equals 7 incorrect predictions. That's a great job the KNN did here, and these are the number of correct predictions. So okay, that's great, and now the best part. Let's look at the result. Let's see the prediction boundary to see if it's a linear classifier. Do you guess if it's a linear or a non-linear classifier? That means, if it's a linear classifier, the separator is going to be a straight line. And if it's a non-linear classifier, the separator is going to be, some kind of a curve. So let's see what it is. Let's just change the title here. We put classifier here because it's the template. But here we will choose KNN. Alright, and let's do it also for the test set so that we don't forget. Classifier, okay, KNN. Alright, now it's ready. It's all good. Yeah, so basically the only thing we need to change is the classifier here. We need to create a classifier and then only to change the title here because we want to specify which model we are using. So let's select everything from here to here and then press Command and Control plus Enter to execute. And here we go. Wow, wow, okay. Yes, perfect. That's a great prediction boundary, isn't it? I mean, it looks so different from what we saw in the logistic regression. Let's enlarge this to interpret the results. Alright, so here are the results. Okay, so the prediction boundary is quite special. As you can see, it's it looks like a boundary of a state in the United States or a boundary of a country. It's actually not even a straight line or a beautiful curve. It's having all those irregularities everywhere. But well, that's the KNN. That's because it's based on finding the K closest neighbors each time. So the prediction boundary for the KNN is most of the time going to look like this. And compared to the logistic regression, we can see that this classifier makes a terrific job classifying the users into their right categories. As we can see here, all the red users that are the users who didn't buy the SUV are in the red region. That means that the region where our model predicted that the users don't buy the SUV. And we see that most of the green points here are in the green region where the classifier predicts that the user buys the SUV. And remember, for logistic regression we had a straight line, so it couldn't classify correctly all those green users here that correspond to users with a age above the average and a salary below the average, but who bought the SUV anyway because the SUV is really cool and cheap. And the logistic regression couldn't catch these guys in the right category because it was linear, and below the line was the red region here, which contained those green users. So there were incorrect predictions. But here, since the boundary is not a straight line and it's catching all the right users in the right category, well, this time KNN classifiers could catch correctly those users and put them in the green region. So that definitely made a terrific job. And then of course we have some incorrect predictions, like the green users here. We can see some green users in the red regions here. So for example, this user, this user, this user, this user. So that's okay, that's because the default parameters for KNN are selected in such a way that we're preventing overfitting in the model. They were selected in such a way that the KNN algorithm didn't fit too well to the dataset. So that's fine. Actually, that's a great model. That's a great classification. Okay, but that's the training set, and that's where our model learned how to classify the data. So let's see how it classifies the data on the new set, that is on the test set. The title is all good, so let's select this and press Command and Control plus Enter to execute. And here is the test set. So let's enlarge this. And here's the test set. And as we can see, these are also great results. Great results. Of course, the regions are the same as we observed in the training set results, because these are the regions that were generated from the learning of the algorithm on the training set. So here we're just looking at some new observations, but the regions remain the same. And so we can see that these regions are perfectly fitted to the tested observations, which are new observations, because we can see that most of the red points, which are the real observation points, are in the right region, right prediction region, which is the red region, and most of the green points are in the right region, which is the green region. So the truth is going along with the prediction. And of course we have some incorrect predictions, but that's because we prevented overfitting. So for example, we have this one, this one. We actually can count the number of incorrect predictions we counted in the confusion matrix. Remember, we had 7 of these, so let's count them. It's very quick. 1, 2, 3, 4, 5, 6, and 7. Alright, so that's the incorrect predictions, but that's totally fine. Okay, so wow, we discovered a new classifier here. It's very different from what we saw in the logistic regression. So the thing that you must remember now, must understand, is that the logistic regression was a linear classifier, and therefore it was a straight line separating the two classes. But now the KNN is a non-linear classifier, so that way it can separate the data even when the data is not linearly separable, which is the case here. So thank you for watching this tutorial. I hope you enjoyed discovering the KNN model, and I hope you enjoyed this graph. I can't wait to show you the next classifiers. We're going to have other surprises. So we're going to have surprises when we see especially the decision trees and random forest classifiers. We're going to have more beautiful decision boundaries, especially when we look at the kernel SVM classifier. So I can't wait to show you this. And until then, enjoy machine learning. Hello and welcome to this R tutorial. Today we're going to implement the K nearest neighbors classifier on R. So let's start right now. The first thing we're going to do is to set the working directory. So right now I'm on my desktop. We're going to go to Machine Learning AZ folder, part 3 classification, and then section K nearest neighbors. Alright, that's the folder we want to set as working directory. Make sure that you have the social network add CSV file, and if that's the case, you're ready to click on this more button here to set the folder as working directory. Here we go, that's done. And now we're going to use our classification template to be efficient and generate all the results in a flashlight. So I'm gonna select everything from here to the top. There you go, copy, and paste it here. Right, and now we need to change a very few things. First we need to create the classifier here, and we just need to change the titles of our plots in the training set results and the test set results. So let's do this right now so that we don't forget. I'm going to replace classifier by, so it's K and N, so we're just doing this to specify the algorithm that we're plotting. And here as well, classifier is replaced by K and N. Right, and now what we only need to do is to create our classifier. But first let's select and execute the pre-processing steps. So I just need to select everything from here and then press Command and Control to plus Enter to execute. That's done. Alright, so we have our data set. We can have a look. That's our data set, our training set, and our test set, which are well scaled. Okay, so As a reminder, the dataset contains information about users in the social network. The social network has a business client, which is a car company, that puts ads on the social network, and the social network gathered not only the information like the age and the estimated salary of those users, but also took the response to these users to the ad, that is 0 if the user didn't buy the product, the car, and 1 if the user bought the product. So it's a very cool luxury SUV launched at a ridiculously low price. So a lot of people, when they saw the ad, said, let's do this, let's get the car. And you can see there are a lot of buyers. So yeah, as you can see, it must be a very cool car and cheap. So now let's go back to KNN and create our classifier. So the classifier is a KNN classifier, and to create this, we're gonna first import the right library. We need a library for this, which is, by the way, called class. So let's do this. So if by any chance the class library is not in your packages list, you need to install it using this command, install.packages, and in parentheses and in quotes the name of the class, which is class. But I think you might have it by default, but if that's not the case, please write this command with class inside, then execute and it will install it. But so here we're just gonna write library and in parentheses class. So that selects automatically the class. You see that right now the class package is not selected, and once this is executed, it will select it automatically. Alright, and now we're gonna do something a little different, because usually we create our classifier here, and then we create this vector of prediction ypred using this predict function that we apply on our classifier and on new observations in the test set. But here it's like we're gonna do these 2 steps all in once, because we're actually going to remove this line, and we're actually going to replace this comment fitting K and N to the training set and predicting the test set results, because all in once we're going to fit K and N to our training set and predict if the users of our test set buy, yes or no, the SUV. So you're going to understand why. We're going to directly create our vector of prediction ypred here, and then before we had classifier equals then the SVM or logistic regression. Here it's going to be directly ypred equals KNN, because actually this KNN function here will return the predictions of the test set observations. Okay, so now let's have a look at this KNN function and you'll get it. So press F1. Okay, so K nearest neighbor classification. Let's first input the arguments. The first argument is train. So you can guess that by train they mean the training set. So here we need to specify what the training set is, and actually since we call it training set, it's training set. So training set here. Alright, training set. However, the training set, as you can see, contains the independent variables and the dependent variable, and we only need to take the independent variables. We won't include the dependent variable in the KNN function here. So here we need to take only the first 2 columns. So we're going to add a bracket here and then comma, because on the left of this comma is all the lines that I'm taking, all the observations, and at the right of this comma is the columns I want to include in the training set. So it's all the columns except for the last one. So I'm going to put here -3, which means I'm removing the last column of my training set. Alright, so that's done. That's what we have to input for train here. So train is your training set, but without the dependent variable. Then comma, and then let's add the second argument. So the second argument is test. So you can guess what it is. It's going to be the same. Test equals test set, of course. Alright, so test set. And then same as training set, we're going to remove the dependent variable, because anyway, we are supposed not to know the results. We want to predict the observations of the test set, so we need to remove it. So comma to take all the lines, and -3 to remove the last column. Okay, so we have our training set and our test set. And now, what is the next parameter? Okay, the next parameter is CL, factor of true classifications of training set. So, can you guess what it's going to be? Okay, let's see. CL equals, in your opinion, what is it going to be? Well, you know, to train a classifier, the classifier needs to have, okay, the independent variables, but it also needs to have the dependent variable because it needs to have the results to, you know, find the correlations between the informations of the independent variables and the information contained in the dependent variable. So here, since we only have the info about the independent variables, we also need to include somewhere the info of the dependent variable. And that's what we add here. That's the CL, so factor of true classifications of training set. That is the categorical dependent variable. So let's do this. So to take this vector actually, so as you can see, that's the last column of the training set. So it's going to be training set, taking all the lines, all the observations, and then the 1, 2, 3, so third index of the column purchased. So let's take that, training set, bracket, comma, and then 3, because the column we want is indexed by 3. Alright, so that's for the third argument, and then we have one more argument, which is the number of neighbors. So let's add this one. So remember in Python we took 5 neighbors. That's actually the default parameter. So here we're going to take the same that will allow us to compare the results we obtain on Python and R. So it will be interesting. So let's take k equals 5 neighbors. Alright, now we have everything we need. We can select this, and here it is, ypred, all good. So now let's have a look at ypred. We can have a look here, ypred. I'm pressing ypred in the console and press enter to have a look at it. And here are all the predictions for the test set. So remember, the test set contains 100 observations. So here we have 100 predictions corresponding to the same observations as these guys here. So for example, let's take the first observation, the first users. So let's take the 1, 2, 3, 4, 5. So the 5 first users. These 5 first users didn't buy the SUV in reality because the purchased variable equals 0 here, and that's the truth. That's what actually happens in reality. And what does our prediction say? 1, 2, 3, 4, 5. 5, 0 here. So correct predictions for the 5 first users. Okay, perfect. Then we have 4 ones. The 6, 7, 8, and 9 users actually bought the SUV. So great for the 6th one, the 7th one great, correct prediction, 8th one correct prediction as well, but the classifier made a little mistake here. That's fine, it looks like it's making some correct prediction most of the time. And we are going to check that on the confusion matrix, that will be faster. It was just to, understand, to explain what ypred was, but I think you get it. So here we just need to select this and execute. Here is CM, we can have a look at it in the console, CM, and that's the predictions. Okay, so we have 6 plus 5 incorrect predictions, so that's 11 incorrect predictions. So that's not too bad. And now what we're most interested to see is the prediction regions, how they behave, and especially the prediction boundary to see if it's going to be a straight line or something else. And actually you're going to see that the KNN is a non-linear classifier, so we will get something different than what we got for logistic regression. So I know it's supposed to be a template that works for every classifier, but the KNN classifier will be the only classifier we will need to change something in the template, besides the title I mean. And that's because of this structure we changed here, For all our classifiers we had this first section where we create our classifier with the classifier equals, and then we create our classifier with a function, and then in another section we create a ypred using the classifier we built in the section above. But here since we did both at the same time, we just need to change a little thing here in the template. So can you guess what it is? Okay, so it's actually in this line, because as you can see here, we are using the predict function on our classifier. But here, since we didn't create a classifier separately from the vector of prediction ypred, well, that means that this predict classifier doesn't mean anything here. So actually it's really simple. What we only need to do is to replace this predict classifier new data equals grid set by this code here, because this is actually like the predict function, only it's creating the classifier and making the predictions at the same time. So there is not a predict function here. So it's very simple. What we only need to do is to take this, Command C, and here, you know, since it's all the predictions of the pixel points in the grid, we will need to change this new data equals test set, so this test equals test set, by grid set. So basically it will be very simple. We will remove this predict function here and paste that. And here we're just going to replace test set by grid set, because we want to predict if those imaginary pixel points that we picture as imaginary users of the social network will buy yes or no the SUV according to their coordinates in the graph, that is their age and their estimated salary. And then once the prediction is done, it will be colorized in the proper color. Green if this imaginary user pixel point is predicted to buy the SUV, and red if it's predicted not to buy the SUV. And that's it. That's all we need. So we're going to select this as well and paste it here to do the same for the test set. Of course it's the same. And here we go. And then we're all good to plot the results. So let's do this. We're going to select this and let's see what we obtain. Command and Control plus Enter to execute. The graph, the plot is coming. You're going to see how the KNN manages to classify the two classes of users, those who didn't buy the SUV and those who bought the SUV. And here we go. That's the graph. That's the prediction boundary here. So you can see there are a lot of irregularities, but that's because of the way the KNN model works, because it's taking each time the 5 nearest neighbors. That's all the prediction boundary. These are our two prediction regions, the red one and the green one. All these points here are the real observation points, are real users of the data set, and their real results, whether they bought yes the SUV if it's green, and no, they didn't buy the SUV if it's red. So we can see that most of our predictions are correct because all the red points are in the red region and most of the green points are in the green region. We also see that the KNN classifier makes a much better job at classifying those users here that their logistic regression couldn't classify correctly because it was a straight line and some green points were falling on the red region. So here it's doing a much better job, and all those users with an age above the average and an estimated salary below the average are now well classified in the green region. So very good, but let's not scream victory until we find out about the results on the test set, because since this is the training set and the KNN classifier was built on the training set, we might get different results on the test set. So let's see. We're going to select this. The test set results are ready. Execute. And these are great results. Most of the red points are in the red region, most of the green points are in the green region, and of course we had a few incorrect predictions like these two guys here or these two guys here, but here it looks very good and we have made nice prediction regions. Okay, so that's it for this tutorial. I hope you enjoy discovering this new type of classifier. We are going to discover new kinds of classifiers in the next sections. I can't wait to show you this, and until then, enjoy machine learning.
Hello and welcome back to the course on machine learning. Today we're talking about support vector machines, or SVMs for short. So SVMs were initially developed in the 1960s, then they were refined again in the 1990s, and only now they're becoming very popular in machine learning because they are demonstrating that they can be very, very powerful because they are somewhat different to other machine learning algorithms. And we'll find out how they're special towards the end of this tutorial. But for now, let's understand how support vector machines actually work. All right, so here we've got, as usual, points on a two-dimensional space. For simplicity's sake, we've got just two columns, x1 and x2, and we've got some observations. Some are red, some are green, so we've already classified them. But now, how do we derive a line that's going to separate them? So how do we actually separate these points? Because that separation, or in other words, that decision boundary is going to be very important for us going forward when we start adding new points. So that's the point of our classification. That's the purpose of our classification. We want to create a boundary between these two so that when we in the future add new points that we want to classify that haven't been classified yet, we will know where they will fall, either in the green area or in the red area. So how can we separate these points we see here? Well, one way is to draw a line like that in our two-dimensional space, and then so anything to the right will be green, anything to the left will be red, and if a new point falls somewhere on this space, we will know right away if it's red or green because we'll know where it falls. However, there's another way. We can draw a horizontal line like that, or we can draw a diagonal line like that. We can actually draw another diagonal line, or we can draw another diagonal line. So there's lots of different lines that we can create that will achieve the same result. They'll separate our points into two classes, but at the same time, they all in the future will have different consequences. So when we add new points, depending on where that point will fall, it'll either be classed as part of the green zone or part of the red zone. So we want to find the optimal line, and that's what SVMs are all about. They're about finding the best line or the best decision boundary, which will help us separate our space into classes. So let's find out how the SVM actually searches for this line. Well, the line is searched through the maximum margin. So here you can see a line, and this is the line an SVM would draw. And so basically it's the line that separates these two classes of points, and at the same time it has the maximum margin, which means this distance. So this line is drawn equidistant from this point and this point, and we'll find out exactly why these points in a second. And then the distance between the line and each one of these points, so that's equidistant, and that margin, so the sum of these two distances, has to be maximized in order for this line to be the result of the SVM. And these 2 points are actually called the support vectors. Why they're called vectors we'll also find out in a second, but so basically these 2 points are supporting this whole algorithm. So even if you get rid of all the rest of the points, nothing will change. The algorithm will be exactly the same. So these other points, they don't contribute to the result of the algorithm. Only these 2 points are contributing, and therefore they're called the supporting vectors. You can call them supporting points, but in reality they're vectors, and this is why. Because in a multi-dimensional space, when you have more than just 2 variables, you can have 3, 5, 10, 100 variables. Each point is actually no longer a point because you can't visualize it on a 2-dimensional plane or even a 3-dimensional space, and therefore each of those points that we see here is actually a vector in a multi-dimensional space. So the more general term for points that we see here are vectors, and this is something that is studied in mathematics in university or high school mathematics. And basically, so generally speaking, they're all vectors. Just in this particular example, when we have 2 dimensions, then we can call them points, but in reality they're vectors, and that's why they're called support vectors. So hence these 2 specific vectors are the ones supporting this decision boundary, or this way we're building this algorithm. That's why they're important, and that's why this whole algorithm is called the support vector machine. So now what else do we have here? Well, we've got the line in the middle, which is called the maximum margin hyperplane, or the maximum margin classifier. So in a 2-dimensional space, it's just like a classifier, it's just a line, but actually in a multi-dimensional space it's a hyperplane. And I know it's a bit of a confusing term, but that's what it's called, a maximum margin hyperplane. So those all other ones that we saw were also hyperplanes, but they weren't the maximum margin hyperplanes, and you can check that yourself. So you can draw a different hyperplane here and just check what the margin will be. It'll always be less because this is the one with the maximum margin. And then you've got the green and the red dotted lines. So the green one is called the positive hyperplane, and the red one's called the negative hyperplane. It doesn't really matter in which order you name them, just the point is that one of them is positive, the other one is negative. Basically anything to the right of the positive is classified as the green category or the positive category. Anything to the left is classified as a negative category or the red category in our case. So that's how the support vector machine algorithm works. Of course there's some complicated mathematics behind it, but the essence, the intuitive part of it is exactly this, that we're working with a linearly separable data set where we can actually, it's given to us by default that we can put a line through our chart which will separate the 2 categories, and then we're just searching for the one with the maximum margin. So conceptually, when you think about it, it's actually a pretty simple algorithm when you think about it this way, without going into the mathematics. And the question is, what's so special about SVMs? Why are they so popular, and why are they different to other machine learning algorithms? And that's exactly what we're going to talk about right now. So imagine you're trying to teach a machine how to distinguish between apples and oranges, how to classify a fruit into either an apple and orange. So you're telling the machine that, all right, I'm going to give you some test data. So have a look at all of these apples. These are apples, these are oranges. Analyze them, look at them, see what parameters they have. And then next, I'm going to give you a fruit, which will be either an apple and orange, and you're going to need to classify it and tell me whether it's an apple and orange, right? So that's kind of a standard machine learning problem. Now, in our case, here you can see, let's say on the right we have oranges, on the left we have apples. So what predominantly machine algorithms would do is they would look at the most apple-y apples and the most orangey oranges. So they would look at the most stock standard common type of apples and the most stock standard common type of oranges. And in our case, it'd be apple somewhere there in the very heart of the apple class, far away from the oranges, and for the oranges would be somewhere over there, so also in the very heart of the orange class, far away from the apple. So a machine would try to learn from the apples that are very like apples, so it would know what an apple is, and it would also try to learn from oranges, so it would know what an orange actually is. And that's how most of the machine learning algorithms work, and then based on that it would be able to come up with some predictions and classifying for new data elements and new variables that you would give it. In the case of support vector machine, it's a bit different. Instead of looking at the most stock standard apples and stock standard oranges, what the support vector machines do is they actually look at the apples that are very much like an orange. So here you can see an apple which is not your standard apple, it's orange in color, right? So it's very easy to confuse this apple with an orange. And they would look at oranges which are not stock standard oranges, which are more like apples than anything else. So ignore the lemon here, it's not supposed to be in the image. Just out of the oranges, the SVM would pick the one that looks the most like an apple. In this case, we have a green orange. It's not normal to have a green orange. When you think of orange, you think of orange. And so what that is those are the support vectors. So the support vectors, you can see that they're actually very close to the boundary. So they're very close to the apple, or the red one would be very close to the green ones, and the orange or the green mark here would be very close to the red ones. And therefore the support vector machine, in that sense, you can think of it as like a more extreme type of algorithm, a very rebellious type of algorithm, a very risky type of algorithm, because it looks at the very extreme case, which is very close to the boundary, and it uses that to construct its analysis. And that in itself makes the support vector machine algorithms very special, very different to most of the other machine learning algorithms, and that's why at times they perform much better than non-support vector machine algorithms. So there you go. I hope this explanation and intuition of support vector machines was useful, and now not only you know how they work, but also why they are different to other algorithms out there that are used in machine learning. And on that note, we're going to end today's tutorial. I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k-nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k-nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k-nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. Today we're going to implement support vector machine, or most commonly called SVM, on Python. So let's start right now. We're going to go to File, Explorer to set our folder as working directory. So we go to Classification, then Support Vector Machine, and here's the folder. Make sure that you have the social network add CSV file, and you can click on this button here to set the folder as working directory. So let's start now. We're going to use our classification template to be efficient and get all our code almost ready, because we will only have a few things to change. So here I'm pasting all the template, and now we need to change a few things, very few things. We need to create the classifier here, which will be the SVM classifier, and then below we will need to change just the titles of the graphs. So here we're going to replace classifier by SVM, and same here, classifier by SVM. And now what we only need to do is to create our classifier. So here I'm going to replace SVM as well. Right. Okay, so same as usual, we're going to import a class from a library, and then we're going to create an object of this class, and then we will use the fit method of the class to fit the classifier to our training set. So let's do this. The class we have to import is SVC, and we are going to import it from scikit-learn.svm. So here we type from sklearn.svm, here it is, import SVC. Alright, so that's the class, and now let's create an object of this class. So we're gonna call this object classifier as usual. So let's do this, classifier equals, and then we're gonna call the class SVC, and now we're gonna input the parameters. So let's inspect the SVC class and let's see what the parameters are. So Command or Control plus I to inspect. And here are the info about SVC and the parameters. Okay, so the first parameter is C, so that's a penalty parameter which we won't need right now because it's to improve the model if we need it, and that we will see at the end of this part. However, there is this important parameter here which is the kernel, and since we're starting with the basic SVM, with a linear kernel, here we're going to specify that we want the linear kernel, because as you can see, the default value for kernel here is RBF, which is the Gaussian kernel. you can see that there are several kernels, like the linear kernel, the polynomial kernel, the RBF kernel, which is the Gaussian kernel, sigmoid kernel. Well, there are a lot of kernels to try. I invite you to test them all. You're gonna have some interesting results. But let's start with the basics. Let's start with the most simple kernel, which is the linear kernel. And as you can guess, this will make our classifier a linear classifier that will look like the logistic classifier. So here, let's input the first parameter, which is then kernel. And let's set it equal to linear. All right. And now, what is the second parameter? Okay, so the degree here is in case you chose a polynomial kernel, then you can choose the degree of your polynomial kernel. So here we're not concerned with that. Then gamma is another parameter in case we chose an RBF, poly, or sigmoid kernel. So we don't care about this one either. And then we have some other parameters that we won't include in our classifier. Actually, we will only include this random state parameter, which is the last one, in order to all get the same results. Well, you're welcome to choose another random state or not to include a random state, but it's just, you know, if you want to have the same results as mine so that you can follow more easily what I'm describing on the graphs, on the following graphs that we're going to plot. So here we're just going to add the random state and we will set it to 0. And that's it. The classifier is ready. And now let's fit it to the training set. So as usual, very simple. Classifier dot fit. So here I'm taking the fit method, and then we will fit our classifier to the training set, that is X train and Y train. And it should be ready. So now let's execute the code. So we're going to first execute this part, which is the data preprocessing part. So let's do this. Here we go. Now the data is all well preprocessed. Perfect. And now we can execute this part, which is the fitting of the SVM to our training set. So let's do this. Ready? Execute. Perfect. Everything looks great. So here we have all the default parameters that were selected because we didn't specify them. So that's all good. We can have a look at our variables in the Variable Explorer. Here we have our data set, the training set, and everything looks great. Okay, and then now that our classifier is ready and fitted to the training set, we can predict some new observations. And these new observations are, as usual, the test set observations. So here we can execute this to get the vector of predictions. Here it is. Now let's have a look. YPred, and let's also open YTest. Alright, so here is YTest, here is YPred. So these are the true results. These are the results that really happened. Did the users really buy the SUV, yes or no? And here, the predictions. Did our model predict that the users buy yes or no the SUV? So let's see, it looks good. From this, it looks like there's only good predictions. Let's have a look. So the first 6 users didn't buy the SUV, and our model predicted well that they didn't buy the SUV, so that's great. 7th user, yes. Yes here as well, perfect. Now let's look at the first mistake, let's see. Okay, so, wow, everything looks great. That's kind of unusual. Let's see, okay. Wow, what's wrong here, what's happening? And here is the first incorrect predictions. I find that a little weird because I thought that this was the first model that was 100% right, which is very rare. I mean, you will never have a model that is 100% right. And by the way, there's this saying that says all models are wrong, but some are useful. So here is our first incorrect prediction to prove this. So yes, there's this mistake here, incorrect prediction for the 31st user of the test set. So this 31st user bought the SUV in reality, and our model predicted that this guy wouldn't buy the SUV. So that's the first incorrect prediction. Okay, so let's press OK, OK. And now let's have a better look at the incorrect predictions in one shot by looking at the confusion matrix. So from what we saw comparing YPred and YTest, this looks really great. So I'm curious to see how many incorrect predictions we have. So let's select this part about making confusion matrix and execute. And now let's see, confusion matrix right here. Oh, okay, so I guess it was just a coincidence that all the first observations had good predictions, because we still have 10 incorrect predictions. 8 plus 2, here are the incorrect predictions. But that's not too bad. 10 incorrect predictions on 100 observations is not that bad. So yes, like 10%, it's okay. Besides, it's on new observations, it's not on the training set where the model was built. So okay, and now time for fun, time for the best part. We're gonna visualize the training set results. So now we would like you to think and try to predict what is going to happen on the graph. We already know that we chose a linear kernel, which suggests that our SVM classifier is a linear classifier. So try to picture, try to guess in advance what the prediction regions are going to be and what the prediction boundary is going to be, and then let's execute the code. Okay, so you can pause the video. I'm going to execute the code right now. So first I'm starting with the training set results. The title was replaced, everything was good. We are ready to plot the results. So let's do this, Command or Control plus Enter to execute. And here we go, SVM. I'm going to enlarge this. Alright, so that's our training set results for the SVM. So did you guess in advance that we would obtain a straight line here? Well, of course, that's because we chose a linear kernel, so the SVM is then a linear classifier, and as explained in the logistic regression section, a linear classifier in a 2D dimensional space is a straight line. And as the data is not linearly separable, it's making some incorrect predictions here, because you know those green points here are users that are aged a little over the average and have a salary a little below the average, but don't fall into these same category as these guys who didn't buy the SUV, they actually bought the SUV. But since the SVM is a linear classifier, then it's a straight line, and therefore it couldn't make a curve to, you know, contour all the red data points this way so that these green points would fall in the green regions. So that's the incorrect predictions, and same as here we have some incorrect predictions. As you can see, these are the green points, so the users who really bought the SUV were predicted not to buy the SUV because they are in the red region. Alright, so interesting, but actually it's kind of the same thing as logistic regression. So, you know, we started with logistic regression, we improved the model with KNN, K nearest neighbors, and now we kind of went back to the lower level, but don't worry, next time we will build a more sophisticated SVM, because we're going to choose a different kernel, which is going to be a Gaussian kernel, so this will make our SVM non-linear classifier, and you will see how it will make a terrific job. So actually you can try to do that yourself, it's quite simple. You just need to take the SVM code again and try to play with the new kernels. Well, you can actually try the Gaussian kernel, RBF, or the polynomial kernel, or even the sigmoid one for fun. But if you choose a linear kernel for SVM, you will get this result. And so it's going to be the same for the test set results. If we look at them, we're going to also obtain a straight line. Well, because actually this won't change, because this is the prediction boundary built on the training set, but this won't change. But our test set results are actually going to be the same. If I enlarge this, alright, as you can see, it's placing most of the red users that are the users who didn't buy the SUV in the right prediction region, and the green ones in the right green prediction region, but it's still making some incorrect predictions here, because we have those same guys who are a little older and a salary below the average who still bought the SUV because the SUV is really cool and cheap. So yeah, that's the same result as logistic regression. So I look forward to showing you what kernel SVM can do, because this will make a terrific job. Because it will even be better than KNN if we are concerned with aesthetic, because as you remember, the KNN had a lot of irregularities. Here we're going to obtain a beautiful curve that will classify well all the data points. Well, not all the data points, but most of them, and especially these guys here, who won't be incorrect predictions. So I look forward to seeing you in the next section about kernel SVM after we complete SVM on R, and until then, enjoy machine learning. Hello and welcome to this R tutorial. Today we're going to implement support vector machine, or more commonly called SVM, and after having implemented it on Python, we're going to do it on R. So let's quickly set the folder as working directory, machine learning AZ, part 3 classification, SVM, and here we are. Make sure that you have the social network ads.csv file, and then you can click on this more button here to set the folder as working directory. All good? Now we're going to go to our classification template that we made in the logistic regression section. So let's take everything from here to the end, copy, and let's paste it in our SVM file. Here we go, and now we need to change very few things. So first we need to create our classifier here, which is going to be the SVM classifier, of course, and then we just need to change the title here for the graph, the training set results. So we're gonna specify that it's the SVM classifier. Same for the test set here, SVM. And now let's move back up to create our classifier. Okay, so as usual, we're going to import a library, and this time the library is going to be the most popular library that is used for SVM, which is the library E1071. So there are actually two very popular libraries. It's E1071 and KernLab, and actually I tried them both. We obtained kind of the same results. So you can try the other one too, KernLab. It's actually almost the same parameters. You just need to press F1 to look at the parameters onto KSVM, because the function for KernLab is KSVM, and you can check it out. But right now we're going to do it with E1071. So let's do this. First, let's have a look at the packages here. Check out to see if you have the E1071 library. It is installed on my RStudio because I used it a lot of times, but if you installed R for the first time, then you might not have it. So I'm gonna just write this command here for those of you who need to install it. So install.packages, here it is, and then in parentheses you put in quotes the name of the library, which is named this way, E1071. Alright, so if you select and execute this line, it will install the package. I won't do it because it's already installed, but it will do it, I promise you. So I'm going to put that as comment there, and now let's start creating our classifier. Well, first we need to, add this line, library E1071, and that's in case you want to make some automated script that select automatically your library here, because this won't be selected all the time. So you want to make sure that you select it. And now we are going to create our SVM classifier. So as usual, we're going to call our classifier equals, and then here we're going to use very simply the function SVM. So let's do this, SVM. Then let's press F1 to look at the parameters, F1, and here are the parameters, the arguments. So the first argument is formula. So let's add it. So as usual, it's the formula that is the dependent variable expressed using the tilde with respect to all your independent variables, which you represent by a dot. So here we're just going to add formula equals. So first we take our dependent variable, which is purchased. All right. And now we use this tilde here, and then a dot. A dot meaning that we're taking all the independent variables of our data set. Okay, now comma to go to the next argument. Then the next argument is data. So of course that's the data on which you want to train your classifier, on which you want your classifier to learn the data to make the future classification. And of course this data is our training set. Okay, perfect. Comma, let's go to the next argument. The next argument is X and Y, but we don't really care about that. And however, we do care about the type here and the kernel. Because the type, as you notice, there's two types of SVM. There's the SVM for classification and the SVR for regression, which is kind of the same support vector machines algorithm, but there is one for classification and one for regression. So here with this argument type, you choose the classification. The default type for classification is C classification. So that's the one we're going to choose for type. Let's add here type equals C classification. Alright, and now the last very important argument is the kernel. So we're starting with the basics. We're starting with the most simple SVM, which is the linear SVM. So here we're going to choose the linear kernel. the linear kernel. And then we're gonna try some more sophisticated SVM with some Gaussian kernel. So I will let you find out about the surprise. You can actually try to practice by yourself and play around with the different kernels. If you wanna, do the course in advance, that's actually a very good thing, to do a course in advance and then watch the course to compare your work with the content of the course. But for now, we're gonna choose a linear kernel. So here we'll input kernel equals linear. All right, and that's all. With these 4 arguments, our classifier is ready. Our SVM classifier is ready. So we're going to select the different steps of our sections of our code. So let's first select this one to pre-process the data. Here it is. Okay, so perfect. We have our data set here, our training set, and our test set. So the data set contains 400 observations, which are informations about users of a social network, including the age and the estimated salary. In this column, purchase here tells if yes or no the user bought a car when the user got the ad that the car company put on the social network for marketing campaign purposes. And so our classifier, as usual, is going to try to classify the users into the 2 categories. Yes, they bought the car, and no, they didn't buy the car. Okay, so let's go back to our classifier. So the pre-processing is done, and now we're going to create our classifier. Everything should go well. I don't have to select this because mine was already selected. So let's press Command or Control plus Enter to execute. And here it is, classifier created, all good. Okay, and now we can make some predictions of new observations, which are here the tested observations. So let's do it. Wipe red. Wipe red. All right, so let's have a look at wipe red. Wipe red. So these are all the predictions of the test set observations. That is, for each user of the test set, our classifier predicts if the user buys the SUV or not. So let's compare the predictions with the truth, which are contained in the test set. So this column tells the truth about whether the users bought yes or no the SUV, and this are the predictions. There is our SVM classifier predicted whether each user bought yes or no the SUV. So let's look at, for example, okay, so all these first guys here were predicted not to buy the SUV. We have all zeros until the 103. But here, as you can see, we have some guys who actually bought the SUV in reality. It's the 18, 19th, 20, and 22. So our classifier predicted that they didn't buy it, and the truth is that they actually bought it. So that's incorrect predictions. But let's look at the incorrect predictions in a more efficient way by looking at the confusion matrix. So let's select this line here and execute. And now let's find out about the real number of incorrect predictions. So let's type CM here in the console and press enter. And wow, that's actually a quite large number of incorrect predictions. And by the way, we don't obtain the same results as in Python because we have some random factors in the model, and here we didn't specify a seed, so you might actually have some different results, but the idea is here. So okay, so let's look at now the graph to see how it's doing. So for those of you who actually didn't watch the Python tutorial about SVM, a good exercise is to try to guess what's going to happen. That is, what are going to be the prediction regions, what is going to be the prediction boundary, what do you guess you will see? So I will let you think for a second, you can pause on the video, and right now I'm going to tell you. So as you notice, we chose a linear kernel, which means that our SVM classifier is a linear classifier. So as I explained in the logistic regression tutorials on Python and R, well, the linear classifier in 2D dimensional space is a straight line. So here, I'm telling you this right now, we're going to get a straight line, not to get any disappointment, because I know we improved our model with the KNN before. We obtained a good prediction boundary that caught, those users on the bottom right corner that actually bought the SUV, but who were incorrect predictions for logistic regression. Well, here it's also going to be some incorrect predictions for the linear SVM because it's actually a linear classifier. So let's look at the results right now. Select this and press Command and Control. Press Enter to execute. And here are the results. Okay, so as you can see, that's exactly what I just told you. Those users here with a lower salary and a higher age, well, they actually bought the SUV in reality because the points are green, the points are the real observations. but they fell into the red region here because since the linear classifier is a straight line, it couldn't, make some kind of a curve here to catch all the red points into the right place, and therefore it caught some green points, putting them in the red region. So yeah, that's exactly the same as for logistic regression. Sorry about the disappointment, but don't worry. In the next section we will introduce a new kind of classifier, which will be, well, the kernel SVM with a different kernel than linear kernel. It's going to be a Gaussian kernel, or even we can try some more kernels. Well, you can practice that yourself. It can be very good practice for you. But here, yes, it's a linear classifier, so basically it's the same as logistic regression. And if we look at the test set results, it's going to be the same. Let's have a look. And here's the test set. Okay, so yeah, same thing. Here we have some users of higher age and lower estimated salary who bought the SUV but fell into the red region again because our classifier is a straight line, and that's the best you could do to classify those 2 points and place them into the corresponding category. So a few incorrect predictions here, a few incorrect predictions here. And if you want, you can count the number of incorrect predictions, that is the number of green points in the red region plus the number of red points in the green region, and you will count the number of incorrect predictions we found in the confusion matrix, which was 20 incorrect predictions. But that's great that we have this result, because that gives us the motivation to improve our classifier, improve our model. And that's what we're going to do in the next section, so I look forward to seeing you in the next section and show you how we can substantially improve our classification model. So I look forward to showing you the next level, and until then, enjoy machine learning.
Hello and welcome back to the course on machine learning. Previously we talked about the support vector machine algorithm, and today we're going to talk about the kernel support vector machine algorithm and the intuition behind it. So as you recall, in the support vector machine situation, we had a set of observations which belong to different classes, and the point was to find this decision boundary between them so that any future observations could be identified which class they fall into. And in this case, we can see that there's a decision boundary, and the support vector machine algorithm tells us exactly how to find that boundary. But what happens when we cannot find a boundary? What happens in a situation like this, for example? What do we do here? We can't just draw a line through these points, right? We can't just separate them with a straight line. We can't separate them with a horizontal line. We can't separate them with a vertical line. Whatever we try to do, we cannot separate these points in the same way that the support vector machine algorithm told us to. And so what happens in this situation, and why does it happen? Well, this happens because in this case the data is not linearly separable. So here we've got the two examples side by side. On the left, the linearly separable data, and on the right, the non-linearly separable data. And what the support vector machine algorithm does is it helps us find that decision boundary, or correctly place that decision boundary. But it does have an assumption. The assumption is that the data is linearly separable. So basically it's saying that it is possible to place the decision boundary. So the support vector machine algorithm helps us choose the optimal decision boundary out of the multiple decision boundaries that we can draw. Whereas in the non-linearly separable case, we can't even draw one single decision boundary or linear decision boundary. So therefore the support vector machine algorithm just won't work by definition. And so what are we going to do? Well, this is what this section is about. This section is about coming up with an algorithm that will help us deal with situations like that, where we have to extract this class when it is surrounded, or in other situations where you can't just simply draw a line. And the way this section is structured, or the intuition tutorials of this section, is first of all we're going to explore a method which is called going to a higher dimensional space, where we will learn how we can take this data set and add an extra dimension into our space that we're dealing with, and make our data linearly separable. So we'll have a look at a couple of those examples, and then we will discuss the kernel trick, which allows us to do these things in a more computationally efficient way without having to deal with multiple or higher dimensions. And finally, we will talk about the different types of kernels that exist. So quite an interesting section ahead, and I can't wait to see you in the next tutorial. Until then, happy analyzing. Hello and welcome back to the course on machine learning. In today's tutorial, we will find out how we can take our non-linearly separable dataset, map it to a higher dimension and get a linearly separable dataset, invoke the support vector machine algorithm, build a decision boundary for our dataset, and then project all of that back into our original dimensions. So quite a lot to cover. Let's get started. First off, we're going to look at a simplified example. We're going to look at a one-dimensional dataset. So normally we visualize everything in the PowerPoint with 2 dimensions to make it look pretty, and so that we can kind of understand how it would work in multiple dimensions. But right now that will be a bit too complex for us to start with, so we're going to start with a single dimension. So here we've got the x1 dimension, we've got some points here, so we've got 9 data points, and as we can see, they are non-linearly separable. So in this dimensional in a single dimensional space, a linear separator would not be a line, it would be a dot, right? So in a 2-dimensional space, a linear separator is a line. In a 3-dimensional space, it's a hyperplane, but in a 1-dimensional space, it's a single dot. So can we separate the green from the red with a single dot here? No, we cannot. If we put it here, then these will be separated from that. If we put it here, it will be separated from that. So this is a non-linearly separable dataset. Now, how can we apply the method of increasing the dimensionality of this space to make it a linearly separable dataset in a higher dimension? That's what we're going to look at, and it might seem impossible, right? So the first time I learned about this, for me it was like, wow, how can you take a non-linearly separable dataset and somehow magically increase the dimensionality and you get a linearly separable dataset? That sounded like absurd, but it is actually possible, and that's what we're going to see right now. So we're going to create this mapping function on the fly. So let's say that this point over here is around 5. So this is 0 over here, and then somewhere here we've got 5. It doesn't really matter, it can be any number, but just for argument's sake, let's say that this point over here is 5, right? And then it keeps going. So our first step to build the mapping function, there can be multiple mapping functions that you can build. I'm just going to show you one that came to my mind. So the first step will be to go f equals x minus 5, so to subtract 5 from our data set, and that is going to what is that going to do? That is going to move everything to the left. So basically now this is what the result looks like. So if you take 5, you subtract 5 from x, you'll get like these ones will go into negative, these ones will stay in positive. And then the next step would be to square all of that. So f is now equals to x minus 5 squared. So how will that all look like? Well, basically you'll have this squared function going through your chart, and then all of these will be projected onto the function. There we go. So that's what it looks like, f equals x minus 5 squared. And now what we want to do is we just want to see that it is indeed linearly separable. So there we go. There's our linear separator. So in a 2-dimensional space, as we remember, a linear separator is a straight line. And as you can see, this data set became linearly separable in this dimension. I know it's surprising and even a bit shocking, but indeed it is the case. So you can see that we were able to take this line and separate all of the red elements of our data set from the green elements, and that's it. And then what we would do next from here is we would project everything back onto our original space, and we would know how to functionally separate the green from the red. And that is what happens when you map something to a higher dimension. So now, knowing this example and seeing that it works in reality, we can proceed to a higher dimension, to start with a two-dimensional space. So let's have a look. So there's our two-dimensional space, and basically you would apply the same principle. So here you cannot invoke the support vector machine algorithm because it is not a non-linearly separable data set in this space, but then you would apply some sort of mapping function. Like right now, we won't go into detail what exactly mapping function it would be, and again, there could be multiple different options and so on. But basically, based on the previous example, we now know that it's possible. Like we've seen empirical evidence that it is possible to do, and the same thing applies to a two-dimensional space moving into a three-dimensional space. You would map it into a three-dimensional space, and then somehow it would become a linearly separable data set in this space. And here we've got the new dimension, which is Z, and in a three-dimensional space, the linear separator is no longer a line, it's a hyperplane. And so this hyperplane separates the two parts of our data set in the way we want. So the support vector machine algorithm has helped us build this hyperplane, and then basically, so we've got this result. Then we just project it back into our two-dimensional space, and we've got this circle that encompasses our classes, or separates our classes, and there we go, we've got the non-linear separator. So as you can see, we can still, even though we have got a bit of a more complex problem where we cannot directly apply the support vector machine algorithm as we used to, we can still go into a higher dimension and then apply the support vector machine algorithm. And like, we won't go into detail if it's possible all the time, and if there's cases when it's not possible and so on, what you would do there. But the point is that there is a solution that you can explore the higher dimensions, so that this is not a dead end. You can just do that. But there's a problem. There's a problem with this algorithm, and the problem is that mapping to a higher dimensional space can be highly compute intensive. So it might require a lot of computation, a lot of processing power, and the larger your data set, the more of a problem this can cause. And therefore, this approach isn't the best, because you can imagine, like, you have a data set, and then mapping it to a higher dimension, performing all the calculations there, and then coming back to your lower dimension. That can, even for a computer, not just like in our minds as humans, but just like for a computer, that can cause a lot of delays. It can cause a lot of like processing backlog and issues in that sense, and we don't want that to happen, and therefore we're going to explore something else. We're going to explore a different approach, which is called in mathematics the kernel trick. And that approach is going to help us perform very similar gets very similar results, but without having to go to a higher dimensional space. And we're going to talk about that in the next tutorial. It's going to be exciting, and I can't wait to see you there. Until then, happy analyzing. Hello and welcome back to the course on machine learning. Today we will finally find out about the kernel trick. So let's get started. So here we've got the Gaussian or the radial basis function kernel, and those are two interchangeable terms. And now let's have a look at this function. So K stands for kernel, and it's a function applied to two vectors. The x vector, so this is just some sort of point in our data set, and L stands for landmark. I means there might be several landmarks, but we're not gonna worry about I for now. We're just gonna look at this as a landmark, and then that equals to an exponent in the power of minus the double vertical lines mean the distance between x and the landmark squared divided by 2 sigma squared. So I know this might all seem very confusing right now, and you're probably wondering, Kirill, this makes no sense whatsoever. What does this even mean? Well, let's explore this through a visual example. So here I've got an image which represents this particular function for a specific sigma, for a specific landmark, but this is what it looks like in when you visualize it. And so what's happening here is we've got L, the landmark, is actually in the middle of this plane. So in the middle of this two-dimensional space, let's imagine this is the x coordinate, this is the y coordinate. In the middle we've got 0, 0, and that's where the landmark is actually located. And then the vertical here, the vertical axis, represents the result that we get when we calculate this for every other point on this xy axis, on this xy field or plane. If we take any other point, then the results of this calculation, so let's say we put that point in here, and then we calculate the distance to the landmark, and then we square it, divided by 2 sigma squared, where sigma is some fixed parameter that we decided upon earlier. And then we take the negative of that, and then we put the exponent into that power, then we get this result, and that's what it will look like. So let's go through this step by step. Let's look at the tip of this visualization. It's right in the middle of this whole xy plane. And so if you project that back onto the plane, and the bottom you'll have the kernel. That's or not the kernel, that's the landmark. We're going to call it the landmark. That's where the middle of this bottom square is, and that's from where we're measuring the distance. So k, this distance, x minus li, this distance that we're squaring here, will be measured from that landmark. So let's take a point and look at it. So there's a point. It's somewhere on our plane. It's quite far away from the landmark. There's the distance. So we're taking that distance. We're squaring that distance, dividing it by 2 sigma squared, taking it negative, and then we want to see what the result will be. And so how can we confirm that this visualization is actually indeed aligned with this formula? So it's pretty simple. The distance here, let's assume it's quite large, right? So it's quite a large distance compared to some other points that are closer to the landmark. So basically the distance here is a large number. And if we take a large number and we square it, right, we get an even larger number. And then we divide by 2 sigma squared. It's still, assuming it's still a large number. Again, it depends on the sigma, and we'll find out the role of sigma further down in this tutorial. But assuming this is still a very large number, so you've got a very large number here, and then you're saying negative, you're making it a negative, a very large but negative number. So if you take an exponent and you put it into a power of very large negative number, so e to the power of 1, let's say minus 1,000,000, right? You know, just for argument's sake, or minus 1,000. What does that give us? That gives us a value very close to 0. So it's basically equivalent to saying 1 divided by e to the power of 1,000, and that is a very, very small number. So that basically means when you're far away from the landmark or from the center, you get pretty much 0 on the vertical axis, and which aligns with our image here. Now let's have a look at another example. So this point is actually closer to the landmark, and here if we measure the distance, it's quite small. So now if you take a small number, you square it, and you still have a small number, you divide by 2 sigma squared, you still have a small number. So you look at e to the power of minus a small number. So let's say e to the power of minus, I don't know, like point or e to the power of minus 1, for example, or e to the power of minus 0.1. So that basically means, so this number is close to 0. It's as you get closer to the landmark, this number gets closer to 0. So, and we know that e to the power of minus 0.01, 0.0001, and so on. Basically, as you get close to 0, e to the power, we get closer to e to the power of 0, and e to the power of 0 is 1. So basically, as you get closer to your landmark, this number over here, this number here gets smaller and smaller and smaller, and this the whole right part over here converges to 1. So it becomes bigger, 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 and you climb this hill up to the top, where you get to 1 at the very landmark itself. So when you exactly hit on the landmark, you get to the top. And so that is just a quick way of checking that this image is indeed the kernel function that we're looking at. And why is this all useful? Why do we need this? Well, because we're going to use this kernel function to separate our data set, to build that decision boundary. So let's have a look. There is our two-dimensional space, right? And there's our x1, x2, just like we had here, x1, x2. And now what we're going to do is we're going to take the landmark and put it somewhere in our among our data set. And there's a whole methodology on how the machine learning algorithm, when you implement it in R or Python or any other language, how it does it. And we're not going to go into detail on that because we're just focusing on the intuition, but basically there's a way to find an optimal placement for these landmarks. And so the landmark is placed, and next what happens is the distance, as you can see here, the circumference around this kernel function is actually projected here onto our visualization. So what this circumference allows us to do is it allows us to take all of the points that are within that circumference and have them like assign them a value of above 0. So anything outside the circumference, all of this blue stuff, so basically all of these red points, they'll get a value of 0, right, if you apply this function, or a value very, very close to 0. If on the other hand any point falls within the circumference, based on this function, it'll get a value of above 0. And that is how we can separate the two classes, the green from the red. Just if we pick the right sigma, so here we know that sigma actually, well, we don't know that yet, but what's sigma's role is that it defines how wide this circumference is. So if you increase sigma, the circumference will increase. Like this picture didn't change, but it should change it. The circumference here would increase and you'd take more of a space up. Or if you decrease sigma, the circumference will decrease, and therefore you'll take less points. And so basically by finding the right sigma, you can set up the correct kernel function to assign 0 values to all of the points that you don't want in your classification, and values above 0 to the points that you do want in your classification. And that will allow you to separate the two. That will allow you to classify each one. And that in essence is the kernel trick. We have created a decision boundary without actually going into a higher dimensional space, without having to project all of our, or create a mapping function that's going to take us to the dimensional space and do all the computation. The point is we're not doing the computations in the higher dimensional space. We're still doing the computations in the lower dimensional space. Yes, we have this visual representation that involves a higher dimensional space, but at the same time, if you look at the computational part, we were just calculating this formula, and then we're saying if this is greater, if this is equal to 0, then assign class red. If this is greater or equal to greater than 0, then assign class green. If you look at the computation, it's actually happening still in the 2-dimensional space, and that's called the kernel trick. So all of a sudden you can adjust your decision boundary, and it's nonlinear, and moreover you find yourself being able to solve much harder, much more complex problems like this, for example. So here, this is it's a very simplified formula, but if you take two kernel functions, you just add them up. In reality, they have to be coefficients, theta here, and then another theta before. So they have to be coefficients with these, with the kernel formula. It's a bit more complex than that, but in simple terms, if you take two kernel functions and you just add them up, then because the value of this function, if let's say this is kernel or this is your landmark 1, because the value of the function when you get further away, it becomes 0, right? They don't really interfere. So as you move away from this landmark, so this landmark will only encapsulate all of these points around here, and then as you move away, this will be 0 everywhere, right? Everywhere else, including in these points. But then this one will be non-zero close to this landmark. And so if you just add them up, you will get non-zero values for exactly all of those points. and so therefore you can draw a nonlinear decision boundary which even looks like this. And the formula here would be the point is assigned to the green class when this equation is greater than 0, and the point is assigned to red class when this equation is equal to 0. Now again, this is a very simplified example. In reality, this is a bit different. It's greater or equal to 0, this is less than 0, and that's because we have the coefficients, and it is a bit more of a complex mathematics behind it, but we don't really need to go into those depths. The point is that we understand here that we can create this non-linear, very complex decision boundary without having to go into a higher dimensional space. Everything is still happening in those same dimensions, simply because we're applying the kernel functions. And that is why this method is called the kernel trick. I hope you enjoyed this explanation, and I look forward to seeing you next time. Until then, happy analyzing. Hello and welcome back to the course on machine learning. I hope you enjoyed the previous tutorials, and today we're going to talk about the different types of kernel functions. So the final thing that you need to know about the kernel SVM is that the radial basis function, which is also called the Gaussian function, is not the only kernel function that is used in this method. So let's have a look at a couple. So here we've got the Gaussian or the RBF kernel, which we've already spoken about. Then there's also a popular choice, which is the sigmoid kernel, and that's the formula on the right. It's in a bit of a different notation, but the essence is the same, is that you still select a landmark, and then from there, depending on the distance to the landmark, different results will occur. But in this case, as you can see, this kernel function is directional, so anything, even like just looking at it in this two-dimensional space, is just a projection. You can see that anything to the right will be automatically right away will have a high value, so will be included in your classification. Anything to the left will be excluded. So sometimes you might require these situations. So maybe if you look at a two-dimensional space, just imagine those points that we had. Points on one side are not in your classification, on the other side are you in your classification. You want to somehow outline that decision boundary, or highlight that points past a certain point should be in your classification, then a sigmoid kernel is a popular choice. Also, we've got polynomial kernels, which are also popular, one of the more popular choices, and here you can have like a polynomial which dictates how your kernel behaves. And again, you can go into more detail on that. So this tutorial is not for us to discuss the specifics of each one of these kernels, but just to show you that they exist and help you be aware of the different types. And so these are the most popular choices: the Gaussian, RBF, sigmoid, and polynomial. And now what we're going to do is we're going to actually go and have a look at them in 3 dimensions. I found a really cool website where we can have a look at that, and we'll go and check it out now. So what I need is, here it is. And so if you go to this website, which is mlkernels.readthedocs.io/en/latest/kernel-functions.html, you'll see some wonderful pictures here. So if you scroll down, you'll be able to find some very interesting different types of kernels in a 3-dimensional space. So you would need to read more about the way they design them, and how the formulas work. So they're a bit different to what we discussed, but nevertheless, the kernel, this gives you a good overview of the kernel functions that exist and that sometimes are used. Probably the 3 that we highlighted would be more than enough for most scenarios that you might come across, but it's always good to know that other types of kernels also exist and they are available to you. So there's the sigmoid kernel, which we talked about as well. So hopefully that's going to be a good overview for you as well. And I'm going to wrap up this tutorial on that note. Hope you enjoyed learning about the kernel SVM, and I look forward to seeing you next time. Until then, happy analyzing. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps need to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. Today I'm super excited because we're going to deal with a very powerful classifier. You're going to see how it will make a terrific job at classifying our users in the social network, and how it will manage to catch those, rebellious users that made our dataset not linearly separable. That's what you need to understand. Our dataset is not linearly separable. That means that we cannot separate the two classes of users in our dataset by a straight line. And so we need more powerful classifiers to overcome this nonlinear separability of the users in our dataset. And we are going to do this with kernel SVM, and I can't wait to show you the results. So here first, let's quickly set the right folder as working directory. So we'll go to File Explorer. Here I'm on my desktop, so I'll go to my Machine Learning AZ folder, Part 3 Classification, and Kernel SVM. That's the right folder. Make sure it has the Social Network Ads CSV file, and if that's the case, you just need to click on this little button here to set this folder as working directory, and you're ready to go. Okay, so what we're going to do right now is we're going to take our classification template that we made in the logistic regression section, a template where we only need to create our classifier and then everything is ready. Once we create the classifier, then we can get a nice coffee, sit comfortably in our chair and watch the results. So let's take all this from here to the bottom, that is everything, copy, and let's paste this template in kernel SVM. Alright, so a quick reminder, this is a data preprocessing step. This is where we create our classifier. Here we predict the test set results. Here we make the confusion matrix to look at the number of incorrect predictions our classifier will make on the test set. And last but not least, my favorite part, visualizing the results. So we're going to visualize two results, the training set results and the test set results. Okay, so let's do this. We're going to start by doing the pre-processing step. So we'll do it all in once. We're going to select this and press Command or Control plus Enter to execute. All good. As you can see, the code executed properly. Everything is fine. We can go to Variable Explorer to look at our data set here, X-train and Y-train for the training set, and X-test and Y-test for the test set. This is the dependent variable. This is the matrix of features. Everything looks great. We can have a quick look if you want to X-train. As you can see, X-train is scaled. Everything looks great. We are ready to move on to the next step, which is to create our kernel SVM classifier. So let's do this. As usual, it's going to be easy. We're just going to use scikit-learn to import the corresponding class for kernel SVM. You're going to see that it's almost the same as SVM. And then we will create an object of this class, which will be the classifier object, and then we will fit this classifier object to our training set. So let's do this. We're going to remove this comment, which was just here for the template. So create your classifier here. Okay, and now let's create the classifier. So we're going to go to scikit-learn and import SVC. So let's do this from sklearn.svm import SVC. Okay. Next, we create our classifier. Classifier equals SVC. Now parenthesis. But before we input the parameters, let's have a look. So we're going to inspect SVC, and to do this, we're going to do Command or Control plus I to inspect SVC. So here we have some information, but what we're mostly interested in are the parameters to see what we have to input. So let's see. Okay, the first parameter is a penalty parameter. We're going to talk about that at the end of the classification part to, improve our model using some penalty parameters or using some regularization techniques. But for now, let's focus on the model itself and get the essential parameters. And speaking of essential parameters, there is one, the kernel. Remember when we used SVM, we used a linear kernel, which made our SVM classifier a linear one. Remember, we had a straight line separating the two classes of users. And here we're going to go a step forward because we're going to use a more sophisticated kernel, which will be the RBF kernel, which is like a Gaussian kernel. So we're going to use this kernel to elevate our data in a new dimension so that in this new dimension our data can be linearly separable and separated by a hyperplane, and then we project back to the two dimensions to get the kernel SVM separate. So yes, we're definitely going to input the kernel parameter. So let's do this. Kernel here equal. So what is it going to be? It's going to be the RBF kernel, which is, by the way, as you can see, the default kernel. Actually, when we talk about SVM in Python, it's by default kernel SVM. But commonly when we talk about SVM, it's the linear SVM. So since it's a default, we don't really have to specify this, but we do this, of course, to remind us that it's a Gaussian kernel. So comma, and then the next parameter. Okay, then what do we have next? Degree. Okay, so that's the degree of the polynomial kernel function. If we choose a polynomial kernel, you can try that yourself. You're going to get very interesting results as well. But here we're focusing on the Gaussian kernel, which is the most popular kernel. So we don't need to do this. Gamma, same for gamma. We will play with the gamma parameter to improve our model, but we don't really need to use it because without a gamma, you're going to see that our kernel SVM will do an awesome job. And so that's it. So we have the essential parameter, that's the kernel parameter, and then we're just going to add a random state parameter. It's a parameter that is, I think, random state here. Random state is here because the kernel SVM algorithm is based on random factors, so we want to use a random state here to all get the same results. And so we're going to input random state equals 0. And that's it, our kernel SVM classifier is ready. How easy was it to do this? So that's pretty cool. So with this line we created the classifier kernel SVM object, and now we need to fit this object to our training set so that our kernel SVM algorithm can learn the data of our training set to learn how to classify the users of the social network. So let's do this. We're gonna take our classifier here and then apply the fit method, which is here, fit, to the training set. And so we need to input the matrix of independent variables of our training set xtrain and the dependent variable vector of our training set ytrain. That's how we have to do it in Python. And that's done. With this line, our kernel SVM classifier will be fitted to the training set. So let's do this. Let's select this and press Command and Control plus Enter to execute. And here we are. Perfect. As you can see, the code executed properly. Here we have all the default parameters that were selected by default in this classifier here because we didn't specify them, but that's fine. Everything is all good. So now that our classifier is ready, let's predict the test set results. So let's just do this and press Command and Control plus Enter to execute. Here we go. Ypred is ready. Let's have a look. Variable Explorer, Ypred, and here is our vector of predictions. So let's compare it with ytest for fun. Here is ytest and here is ypred. So this is the truth, this is the predictions. So let's have a look. We can see already that everything looks, correctly predicted. We have all the zeros here from 0 to 6, same here from 0 to 6. A 1 here in 7, that means that the 7th user of the social network in our test set bought the SUV, and our classifier predicted that this user would buy this SUV. Same for the 8th user. The 8th user didn't buy the SUV, and our classifier predicted that the 8th user didn't buy the SUV. Great again. But let's not celebrate victory yet. We have one incorrect prediction. Well, no model is perfect. Actually, there is one saying in machine learning saying that all models are wrong, but some are useful. Well, that's the case here. This model is definitely useful because it can, classify your users into categories to help the marketing campaigns target their users to sell their product. So this model is definitely useful, but it's wrong, of course, because there will always be some incorrect predictions. You will find some models with no incorrect predictions on the training set, but wait for it. When you test it on the test set, you will find always some incorrect predictions on new observations, which make them wrong. So that's what it is about. And now, as you can see, we can check the last ones just for fun. Okay, 111, 111, 00. Okay, one incorrect predictions on the 95th, but correct here and here. That looks fine. I can't wait to find out the number of incorrect predictions on the confusion matrix. So let's do this right now. Remember, we had 11 incorrect predictions with logistic regression. That will be our reference for comparison. So now let's see the number of incorrect predictions for SVM, kernel SVM. And so I just selected that, and we're going to find out right now. Command and Control plus Enter to execute. And here it is. Can we already see that? Yes, we can. It's actually right here. We have the 4 and the 3 here. So that means we have 7 incorrect predictions. Great. So better than logistic regression, definitely. 7 incorrect predictions on the test set. So that's an improved model, definitely. Let's click on OK. And now you can boil the water and prepare your coffee, or I don't know how you prepare your coffee, but you can get your coffee, because now what we only need to do is to select all this and visualize the training set results. So are you ready? Let's do this. You're going to see how our kernel SVM classifier manages to classify our categories and how it manages to catch those users and put them in the right category, those users that make our dataset non-linearly separable. So let's see, Command and Control plus Enter to execute. And here it is. Wow, beautiful, very beautiful. Let's enlarge this. Okay, so just for those of you who discover this plot for the first time, I'll just remind quickly what this is about. So all the points here are the observation points in our training set. So these are the users of our training set. And these are the true results. So all the points represent the truth, what really happened. Those red users didn't buy the SUV, and those green users, the green points here, bought the SUV. And then we have the regions, which are the prediction regions. So the red region here is the region where a classifier predicts that the user don't buy the SUV. So that means that any user falling in this region is predicted not to buy the SUV by the classifier. And the green region is the region where a classifier predicts that the user will buy the SUV, which means that any user falling in this region is predicted to buy the SUV according to the classifier. So that's the important thing to understand. The points are the truth and the regions are the predictions. And then the next thing to understand is that this separator here, separating the two regions, the green region and the red region, is called the prediction boundary. So before, with logistic regression and SVM with a linear kernel, we had a straight line separating the two categories. But here, since we jumped to a higher level, we built a nonlinear classifier, which we can clearly see here because the boundary is not a straight line anymore, but it's a curve, as you can see, that separates well the data. So now, definitely thanks to this classifier, these older users here with a low estimated salary are now classified in the right region. And same for this younger users with a high estimated salary, they are now well classified. And of course we have some incorrect predictions, which are, for example, here, here, or here. And that's because the kernel SVM is not like an overfitting classifier, you know, like making a curve going all the way here and catching all the points here, doing this. That's because it's a sensible nonlinear classifier. But for example, if we play around and take a polynomial classifier with lots of degrees, you know, you can choose the number of degrees in your parameters for kernel SVM. If you pick a polynomial kernel, well, you're going to see that it's going to be overfitting the dataset because it will try to catch also those green points here by doing multiple curves here. You can try and play around with that. It can actually be pretty fun. But the kernel SVM is a sensible classifier. And this is actually one of the best classifiers you could find in that situation, because you wouldn't want it to overfit your data. Because, okay, there is this green point here in the training set, but what does tell you that we will have the same green point in the test set? And last but not least, what I have to say is that, okay, we see this curve here that separates well the data, but don't forget that there was a terrific job at doing this, because if you go behind the scenes, you can see that the kernel SVM jumped to a higher dimension to, you know, find a higher dimensional space where it managed to distribute our data in such a way that the data was linearly separable in this higher dimensional space. And that is by using this mapping function that Kirill talked to you about. You know, this mapping function that kind of take the data that was originally in a two-dimensional space into a three-dimensional space in which the data is now linearly separable. Then it found a linear boundary hyperplane in this higher dimensional space, that is the 3D dimensional space, and then it projected back to this two-dimensional space to finally obtain this curve here that separates well the data here. Okay, so that's it for the training set, and now let's look at the test set. So I'm going to close that, and then very efficiently select this, Command or Control plus Enter to execute, and here are the test set results. So let's enlarge this, and here we are. So wow, so yeah, that's great too. That's great results as well. We can clearly see that almost all our new observations are classified in the right category. The kernel SVM made a great deal of predictions, predicting that the users wouldn't buy the SUV in this red region and that they would buy the SUV in this green region. That's what happened. Of course, we have the incorrect predictions. Remember, we counted 7 incorrect predictions in the confusion matrix. So here we can count them, it's pretty quick. We have 1 here, 1, 2, 3, and 4, 5. You know, these are the red truth observation points that are in the green predicted region. So these are incorrect predictions. So 4 and 5, and then 6, and finally 7. So yeah, there we are. We have our 7 incorrect predictions. But that's fine. I mean, as I told you during the training set part, that's totally fine. We don't want an overfitting classifier that classifies too well the data, and it's totally fine if we have some incorrect predictions. The marketing campaigns are not to the nearest dollar. So that's a good classifier, and now we can confirm that with this new observations results, since it is well classified. Okay, so that's it. I strongly recommend you to play around with the parameters so that you can already try to improve yourself the models And now I can't wait to show you the next classifiers, which will be the decision tree classifier and the random forest classifier. You're going to see that we're going to discover a brand new style of results. It's not going to be this kind of curve anymore. It will be something else. I won't tell you what it is and let you wait for the surprise. But that's what's so cool about machine learning, is that there is diversity in the models and the graphic results. We always discover some new things. And there is no limit to that. I mean, machine learning scientists and researchers are always thinking of new ideas of machine learning models, so you will always find some new tricks and some new innovative ideas about machine learning models. So that's what's so cool about machine learning. There is not a finite point. It's like the universe expanding to infinite limits. Okay, so thank you very much for watching this tutorial. I hope you liked the kernel SVM classifier. And now wait to see the decision tree and random forest classifier. That will be the subject of our next sections. Thank you for watching this tutorial. I look forward to seeing you in the next tutorials, and until then, enjoy machine learning. Hello and welcome to this R tutorial. Previously we implemented the kernel SVM in Python, and now we're going to do it on R. So for those of you who haven't checked the Python tutorials on kernel SVM, I can't wait to show you the results. It's going to be something. You'll definitely see how the kernel SVM classifier can be a powerful classifier, especially in our situation where the dataset is not linearly separable. Here you're going to see how it can manage to overcome this non-linear separability and classify most of our users of the social network correctly. So let's make this kernel SVM classifier right now and quickly look at the results. So as usual, we're going to start by setting our working directory. So right now I'm on my desktop. I'm going to my machine learning AZ folder, part 3 classification, section kernel SVM, and here we are. Make sure that you have the social network add CSV file in your folder, and if that's the case, you're ready to click on this more button here to set your folder as working directory. Here it is, all good. And now let's start making our model. So we made an awesome classification template. It classifies those users into two categories: the category of users that didn't buy the SUV and the category of users that bought the SUV. So let's do this. Let's do it with kernel SVM, and so right now we need to create our classifier. And as usual, it's going to be very intuitive and simple. We're going to use the best library for this, and besides, if you watched the SVM tutorials, you're going to see that we're using the same library and the same function. We will just need to change some parameters. So let's do this. For those of you who didn't follow the SVM tutorials, you need to install a package. So to do this, you type this command, install.packages, and in parentheses and quotes E1071. So that's the most popular package for SVMs. Another very popular package is KernLab. You can play around and check it out. It's actually quite simple. It's kind of the same function, only with slightly different parameters to input, but it's also a great package for SVMs. But here we're going to use E1071, which is one of the most popular packages. And so that's for you guys who, if you go to your packages list here, and if you go to E1071, you can see that I have this package installed on my packages. It might not be the case for you, so that's why I'm adding this line here in case you don't have the package installed on your packages in R. So I won't do it right now. You just need to select this line and execute, and it will install the package very quickly. So I'm just going to put that in comment. I just pressed Command Shift plus C, and now we need to do another important thing about this library is to type this command library and then in parentheses the name, not in quotes, of the library E1071. Okay, and we need to add this line. It's very important in case we have some automated scripts that make some kernel SVM models to dataset. So imagine you have a workflow and you want to include the kernel SVM model in this workflow. Well, you will need some automated scripts. So it's important to add this line because this will automatically select your library, because as you can see here, it's not selected. That means it's not imported in some way. So you need this line that will automatically select this package. Okay? And now we're ready to create our classifier. So it's going to be the same as for SVM, which is actually an SVM with a linear kernel. Here we're not going to use a linear kernel, we're going to use something else, which will be the Gaussian kernel. So let's do this. We're going to call our classifier as usual classifier. and then equal, and then here we're going to use the SVM function of the E1071 library. And now we need to import the parameter. So as usual, let's have a look. Here it is, and now you need to click on this. And here we are in the R documentation for SVM E1071. Okay, so let's have a look at the arguments. The first argument is formula, so as for SVM it's going to be purchased, tilde, and then a point, and the point represents all the independent variables, so we know this. Then data, okay, so yes, you need to specify the data because you want to specify the data set on which you want to train your kernel SVM model. So we need to specify data equals training set because we are training our model on the training set. Then X, Y, and scale are not important here. What's really important are the type and the kernel. So the type is whether you want to make a regression model, that is SVM for regression, that is SVR that we saw in the regression part, or SVM for classification, which is the common way of saying SVM. So here we will need to specify the C classification type, which is the default type for classification for SVM. Remember in the SVR we chose EPS regression, that was the default type for regression for SVM. But here we are in classification, so we will choose this C classification type. And then the most important is the kernel. Here we jumped to a higher level. We are making a more sophisticated SVM than the SVM we did in the previous section, which was a linear kernel SVM. But now we want to go pro, and we are choosing a Gaussian SVM, which you will see make a terrific job at classifying your users in the social network. Because remember, the kernel SVM was linear, which made our SVM model a linear classifier, and therefore the separator separating the two classes of users was a straight line here, and therefore couldn't catch the users here. That made our dataset non-linearly separable. So here we're going to choose the Gaussian kernel, which is going to be the radial basis kernel. Actually, we're not going to write radial basis, we're just going to write radial, that's how it works, but the Gaussian kernel is radial. Actually, you can see the formula here. Kirill gave you the formula of the Gaussian kernel, and here it is. Okay, so now let's jump back to our code and let's implement this. Okay, so remember the first argument was formula, and then here we have to first take the dependent variable, which is purchased. You know, if you go back to our data set, this is the dependent variable and this is purchased. Then tilde, which is alt n, and then a dot to take all the independent variables of our training set. That is, we're taking age and estimated salary. Alright, then comma to go to the next argument, enter, and then the second argument. So the second argument, remember, it was data equals training set. Okay, and then the next parameter, what was it? It was type. Type equals C classification. Actually, we don't really need to input the type here because it's the default type. But let's specify this to, make the distinction between SVM for regression, SVR, and SVM for classification, kernel SVM here. And then of course, we will add the essential parameter for this section, kernel SVM, which is of course kernel, and that's where we pick our more sophisticated kernel, which is the Gaussian kernel called here radial. Alright, now our classifier is ready, so let's immediately select this. And perfect, our classifier is now built. So now let's use it to predict the test set results. So we're going to select this line simply and press Command and Control plus Enter to execute. And here is our ypred. Let's have a look. Ypred, we type ypred here in the console, press Enter, and here we have all the predictions for the test set. So there are 100 predictions, so let's have a look at the first one. So we need to compare this ypred, which is the vector of predictions, with the true results of the observations, the true results whether they bought yes or no the SUV. And for this we need to go to the test set here to check it out. So let's see. The 1, 2, 3, 4 and 5 users didn't buy the SUV in reality, and our predictor predicted that these same 5 users didn't buy the SUV. So that's some correct predictions, it's a very good start. Then if we look at the next observation, we have one here, one here. So that makes the 8 first predictions correct predictions. And here we have our first mistake, our first incorrect predictions, because for the user number 22, our classifier predicts that this user wouldn't buy the SUV, and in reality it did. If we look at the number 22, we can see that we have a 1 here, which means that this user bought the SUV. Okay, but the best way to look at these predictions is to use the confusion matrix. So let's do this. The section is here already. We don't have to change anything. The template is there to ease our work. So let's select this line. Let's Command and Control plus Enter to execute. And here we have our matrix. So we're going to look at it in the console. So CM here, Enter, and here is the matrix. Okay, so what do we have here? We have 58 plus 32 equals 90 correct predictions, and 4 plus 6 equals 10 incorrect predictions. So that's not too bad. But now the most exciting part is coming, because we're going to be visualizing the training set results. And actually right now we don't have to change anything except maybe the title here, classifier, and then here you need to specify kernel SVM, as well as here in the test set, so here kernel SVM as well. Alright, now we can get some coffee and just execute this and watch the results. So we're going to do this. We're going to first look at the results here and press Command and Control plus Enter to execute. And wow, these are the beautiful results of kernel SVM. We can see how it's making this curve here to classify well most of the users in the social network. Here, since we have a 2-dimensional space here for the dataset, that means that the dataset was mapped to a 3D dimensional space. And then on this dimensional space, it managed to make the data linearly separable so that it can find a linear hyperplane that separates in a much better way the two classes. And then it projected back to this 2-dimensional space to finally obtain this curve here that separates in a much better way the two classes than a linear classifier would do with a straight line here, as we saw for logistic regression or SVM with the linear kernel. So that's what happened. That's what happened behind the scenes. The kernel SVM did an amazing job, so we can say congrats. Okay, so those of you who are seeing this for the first time, I'll just quickly remind what it is. The points here are the true observations, the true results. So the red points are the users who didn't buy the SUV in reality, and the green points are the users who bought the SUV. And then the regions that we see here are the prediction regions. So the red region is the region where our model predicts that the user doesn't buy the SUV, and the green region is the one where our model predicts that the user buys the SUV. So for example, that means that for this particular user, red point, which is in the green region, that makes an incorrect prediction because the truth is the user didn't buy the SUV. But since this user is in the green region, that means that the model predicted that this user bought the SUV, even if that's not what happened in real life. So that's what the graph is about. And here is the nonlinear separator of the kernel SVM algorithm. And thanks to this nonlinear separator, our kernel SVM could classify correctly those users here, which wasn't the case for the linear separators, because since we had the straight lines, it couldn't catch these users in the right category, that is the green category, because those users actually bought the SUV in real life, so they should be in the green region. And this wasn't the case for the linear separator, and now it's the case for the kernel SVM separator, because it's a nonlinear classifier. Perfect, now let's have a look at the test set results to see how our model behaves on new observations, to see if it can still classify and predict the results of new observations. So we're going to do this. We only have to select this, press Command and Control plus Enter to execute. And here are the test set results. Okay, so that looks great as well. First, an important thing to understand is that the regions that we see here are the same regions as we saw in the dataset. If you go back to the training set and then go back to the test set, you can see that the regions here don't change. Only the observation points change, because of course these are new observation points. And so here we can see that the kernel SVM did an amazing job at classifying new observations, because all these test set observations here are the users who didn't buy the SUV, because the points are red, and they are in the red region, that is the region where our classifier predicts that the users don't buy the SUV. So that's correct predictions. Same for these guys here, all the green points that fall in the green region. And of course we have those incorrect predictions, which are, for example, this green user here who is in the red region, as well as those two green here, so that's 3. Then we have the red users, this one, so 4, 5, 6, 7, 8, 9, and actually 10. We can see that there is a little green point here hiding behind the red point. Okay, yeah, so that's definitely a very good job. You will see how the next classifiers will make a different style of classification, of separation. You will see that it won't be a curve, it will be something else, and I will let you find out about the surprise. But definitely the kernel SVM is a great classifier when your data is not linearly separable, and we can see how it definitely improved the results of the linear classifiers that we saw with the logistic regression of SVM. Alright, so thank you for watching this tutorial about kernel SVM. I hope you enjoyed it. There will be a few more surprises with the next classifiers, as I told you, so you're gonna see the results. It's gonna be pretty fun, and so I look forward to seeing you in the next sections. Until then, enjoy machine learning!
Hello and welcome back to the course on machine learning. Today we're talking about Bayes' theorem. Now our main goal for this section is the naive Bayes classifiers, but at the same time we can't proceed to them without talking about Bayes' theorem. That's why we're going to have this lovely tutorial devoted specifically to this topic. So let's kick it off and get straight into it. Today we're talking about spanners. I know it's a bit weird why we're talking about spanners. We're supposed to be talking about Bayes' theorem, but I'm going to be illustrating the Bayes' theorem on an example, and we're going to be using spanners just because it's one of the things that I found on the internet, one of the first pictures that came to mind, and also that way you'll always remember whenever somebody says Bayes' theorem, you'll remember spanner and you'll remember what we talked about today. So it's a good way to anchor this into your memory. Alright, so let's say we're at a factory, we're doing some analytics for a factory, and there's 2 machines, and one machine produces spanners and the other machine produces spanners. Now the machines work at different rates and they have somewhat different characteristics, but overall they're producing the same spanners. The additional information here is that the spanners are actually marked or tagged, so we know which machine they came from. So the top ones came from machine 1, the bottom ones came from machine 2. And then at the end of the day, we've got like a whole pile of these spanners, and the workers go through them, and their goal is to pick out the defective spanners. So here we can see that there's a couple of defective spanners hiding among the pile. Now, the question that we're going to be asking today is, what's the probability? What's the probability of machine 2 producing a defective spanner? So if you take just a random spanner produced by machine 2, so as it comes out of from the conveyor belt, you pick it up, what is the probability that that spanner is defective? And the way we'll get to that probability is through some information that will already be given to us at the start. So we'll have a look at that information in a second, but the rule or the mathematical concept that we'll be using to get to that probability is called the Bayes' theorem. Here's a mathematical representation of it. I know it is a bit complicated right now. It seems like, what are all these signs? Like, we know that P is probably probability, but then B, A, and the vertical line, what are all of them doing here? What is this relationship telling us? Well, don't worry about it for now. We will walk through it very slowly, step by step, and you'll get to know the Bayes' theorem very intimately. All right, so let's get started. What is the information that is provided to us at the very start? Well, we know that machine 1 produces 30 wrenches per hour and machine 2 20 wrenches per hour. By the way, wrenches and spanners, I found out just now that they're actually the same thing. A spanner is outside of North America, a wrench is inside of North America. So there you go, you learned an extra additional thing today. If you didn't know that, I learned an extra additional thing. So we're just gonna call them wrenches from now. Machine 1 produces 30 wrenches, machine 2 produces 20 wrenches per hour. Okay, great. Also, out of all of the produced parts, we can see that 1% are defective. So after checking the parts at the end of the day, thousands and thousands of wrenches, we can see that 1% of them are defective. Okay, so we know that. Then we also know that out of all of the defective parts, we can see that 50% came from machine 1 and 50% came from machine 2. So here you can see that if you take all the defective parts, so only the defective parts, and you calculate how many of them came from machine 1 and how many of them came from machine 2, you'll see that half and half, that half of them are from machine 1 and half of them from machine 2. Alright, so this is just the defective parts. And the question is, what is the probability that a part produced by machine 2 is defective? So that's the same question which we discussed already. What is the probability that if I come up to machine 2 and take the part that just popped out of machine 2, what is the probability that that part is going to be defective? So how do we put all that information together to get the answer to this question? That's what Bayes' theorem answers or helps us do. So let's have a look at how we can rewrite this information in more mathematical terms. So the first line, what does it tell us? It tells us that machine 1 produces 30 wrenches per hour, machine 2 20 wrenches per hour. So in total, out of all the wrenches produced, there's 50 wrenches produced per hour. And also that means that the probability of any given wrench that you pick up from the pile, just any, whether it's defective or non-defective, if you pick up a wrench from the final pile, the probability that it'll come from machine 1 is 30 divided by 50. Right, so if we're producing 30 from machine 1 and 50 overall per hour, that means likelihood of any given wrench to be from machine 1 is exactly 30 divided by 50, or 0.6, or 60%. Similarly, the likelihood of that wrench being from machine 2 is 20 over 50, or 40%. Alright, great, so we're going to write those down and keep them there for now. Now let's see what we can get out of the second line. So we can see that out of all the produced parts, we can see that 1% are defective. Well, it's very simple to rewrite this in mathematical terms. We can just say probability of a part being defective equals 1%. So even though that was a simple transition, actually these sentences are saying a bit different things. So the one on the left says we can see that 1% are defective. So that means that we counted the number of defective parts and we divided by the total amount, and that means that 1% is defective. On the right, we're saying the probability of a single part to be defective is 1%. So that means if I pick up a random part from the pile, the likelihood of it being defective is 1%. Right? So that is what we're saying here, and it's a very simple thing to write in mathematical terms. There it is, P defective, or that there's a defect, equals 1%. Alright, and now we're moving on to part 3. Out of all of the defective parts, we can see that 50% came from machine 1 and 50% came from machine 2. So how do we write that in mathematical terms? And this is the interesting part. So let's start with the machine 1 part. 50% came from machine 1, meaning that if we take only the defective parts, so if it's given that we're only looking at the defective parts, then the likelihood that any part that we pick out, that part came from machine 1 is 50%. And the way to write in mathematical terms is this way. P of machine 1 vertical line defect equals 50%. So the right part over here, the vertical line in mathematical terms means given. So here you can see P of machine 1 means the likelihood or probability of a part coming from machine 1. Here it's the same thing, but given some condition. So this is the likelihood of a part coming from machine 1 given the condition that that part is defective. So you know a priori that that part is defective because you're picking it out of the defective pile. So what is the probability of that part coming from machine 1? Well, it's 50%. And that is the mathematical transcription of this sentence. We can see that 50% came from machine 1, 50% of defective parts. Okay, so now let's do the same thing for the machine 2. It's going to look exactly the same, but here it's going to be machine 2. So probability of a part, that the part that we just picked up, the probability that it originally was created by machine 2 is 50%, given that we're only picking out from the defective pile, right? Because if we're picking out of all of them, it's actually 40%, it's 0.4. But if we're picking it out only from the defective pile, it's 50%. So you can already tell from here, from these two expressions or 4 expressions, that the likelihood of a part coming from machine 2 is 40%, meaning that it produces less. It produces less wrenches. Whereas the likelihood of a defective part coming from machine 2 is 50%. So that if you take any part or any wrench, you pick it out from the defective pile, the likelihood that it was originally produced by machine 2 is 50%. So you can tell right away that machine 2 seems to be producing disproportionately more defective parts than machine 1, right? So it's only producing 40% of the output, but it's accounting for 50% of the defective parts. And the question that we want to ask is actually a bit different, right? So the question we want to ask is, what is the probability that a part produced by machine 2 is defective? So here it's kind of reverse. Here we're saying we're taking a part from machine 2, right? We're only looking at parts that are produced by machine 2, what is the probability of a random part taken out of machine 2 to be defective? How do we write that in mathematical terms? It's written this way. So probability of a defective part given that it came from machine 2. If you look at just the probability of a part being defective, it's 1%. But here we're given a condition that it's machine 2. So the way to think of it, you can either think of it as parts are coming out of machine 2 and you just pick up a random one, what's the probability of it being defective, right? Or you can think of it in terms of quantities. The correct term here is frequentist interpretation. So you can think of it in terms of the frequentist interpretation, and that means instead of just picking up one part and thinking about what is the likelihood of it being defective, if we know that it came from machine 2, think of it as there's a pile of wrenches that only came from machine 2. So you have a pile of 1,000 wrenches that came from machine 2. What is the number of wrenches that are going to be defective, right? So what is the portion of wrenches that are going to be defective? So those are two different ways of thinking about probabilities, or the Bayes theorem, but they're pretty much the same thing. They're exactly the same thing. It's just different ways of thinking about it. So it's either what's the probability of this one part that just came out of machine 2 being defective, or what is the portion of all of these parts that came out of machine 2, what is the portion of them that's going to be defective? So that's the question that we want to answer given all this information. All right, so let's start solving this problem, and we'll illustrate how the Bayes theorem will help us convert this information to this information. All right, so first of all, we won't need the probability for machine 1 and the probability for machine 1 given defective. So we're going to get rid of that out of our information just to clean things up. Okay, and now let's just move everything, slide everything over to make some space. And now let's write down the Bayes theorem, which we had a brief look at before. The Bayes theorem for this particular problem will look as follows. So the probability of a defective part, given that it came from machine 2, so a probability of a part being defective, given that that part, that wrench came from machine 2, equals, and here we go, this is the fun part. So you will take the probability, we'll start from right to left. We'll take the probability of a part being defective overall. We will need to multiply that by the probability that a part came from machine 2, given that it was defective. And we'll need to divide that by the probability of the part coming from machine 2. All right, so for now, this might seem a bit better already than we saw previously. At least now we can read these terms, right? And we know how we got them here. So we actually discussed each one of these terms, and they're pretty straightforward, even though the mathematical representation might look a bit scary. At the same time, they're pretty straightforward terms. We know what we're talking about. At the same time, we don't really understand where this formula came from, and more importantly, on intuitive level, doesn't really make sense at this stage. But it's okay. Let's for now plug in the numbers, and then we'll proceed to the intuitive part of this formula. So if we plug in the numbers, what we'll get is 0.5. So we'll just take numbers from the top, or if we start from right to left again, the probability of a part being defective overall is 1%, multiplied by probability of a part coming from machine 2, given that we're only looking at defective parts, or given that that part is known to be defective. It's 50%, so there it is. And we're dividing that by the probability of the part coming from machine 2 overall, and that is 40%. So there you go. So if we plug that in, we get 0.0125. So 1.25 percentages, or 1.25% is the probability that machine 2 will spit out a defective part, right? So if you come up to machine 2 and you pick up a part, then the probability of that part being defective is 1.25%. Or the frequentist interpretation is, if machine 2 produced 1,000 parts, then according to the Bayes theorem, 12.5 of them will be defective. So you can't really say 12.5 wrenches will be defective. So let's say it produced 10,000 parts, then the Bayes theorem tells us that 125 of those wrenches are going to be defective. So as you can see, we converted all this information that we knew about the process and about the results of the process into exactly what we want. Now let's move on to the intuition, the fun stuff, right? So there's 1.25%. So let's move this to the top. That's our Bayes theorem. And let's look at an example, and you'll see that it's actually very, very intuitive what we just did. It all makes total sense. So let's look at an example. let's say we produced 1,000 wrenches all total. So in total, we have 1,000 wrenches after the two machines were working for some time. So we know that 400 of them came from machine 2, right? So we know that machine 2 produces, how many wrenches per hour does it produce? Produces 20 wrenches per hour, and machine 1 produces 30 wrenches per hour, as per our information from the very start. And that means that out of the 1,000 wrenches, 40% would have been produced by machine 2. That means 400 came from machine 2. Okay, so that makes total sense. Then we also know that 1% have a defect. We actually see this. The workers who look at the wrenches at the end of the day, this was also given to us, they see that 1% have a defect, and that means out of 1,000, 1% is 10. So 10 wrenches have a defect. Okay, great. And so what's the next step? Next step is that we know that 50% of those 10 came from machine 2. So we know that exactly 5 of those defective wrenches came from machine 2. That was also given to us because those defective wrenches actually have labels on them, and we can tell by the labels that 5 of them came from machine 2. Alright, so the question is, what is the percent defective parts from machine 2? Well, it's very easy now, right? Because we know that how many defective actually came from machine 2, 5, and we know how many wrenches came from machine 2, 400, right? So all we have to do is divide 5 by 400 and we'll get 1.25, right? So we get the same answer. Not only do we get the same answer, we actually did exactly the same process. If you think through what we did here, we performed exactly the same process. We had 1,000 wrenches, right? And then we turned that into 400. So we multiplied 1,000 wrenches by 40%, which is the probability of a part coming from machine 2. So this is our denominator, right? So instead of probability of machine 2, what we just did, this 400 is P of machine 2 times 1,000, right? So we have P of machine 2 times 1,000 in the denominator instead of just P of machine 2 in what we're doing here, right? And then 1% have a defect. And that means 10. So where did this 10 come from? That's 1% times 1,000. So instead of P defect at the top, we actually have P defect times 1,000 right now. So just visualize that for a second. So instead of P machine 2, we have P machine 2 times 1,000, P defect times 1,000. And then this 50%, the probability of them 50% came from machine 2, right? Equals 5. This line is actually us performing this operation here. We're saying the probability of card coming from machine 2, given that it's defective, is 50%. So basically, to get to this, what we did is we took this part, so we took 50%, we multiplied it by the 10, which is actually, so we took 50%, multiplied it by 1% times 1,000. So here we've got extra times 1,000, and here we've got P machine 2. What we did is we actually put in P machine 2 times 1,000. So I just added an extra part over here times 1,000 and part over here times 1,000, and then we still divided that final result, that 5 that we got, by the 400 that we got. So the logical steps that we took are exactly the same as the Bayes theorem. The only difference is that we looked at a specific example of 1,000 wrenches. So as you can see, the Bayes theorem is a very intuitive theorem. So we're not even going to go into the mathematics of how it's derived. This is about us understanding it intuitively. So as long as you remember the mathematical representation of the Bayes theorem, it actually makes total sense what it is helping us calculate and in the steps that it is implying for us to take to calculate the final result. So there we go. Hopefully that all makes sense. And we only have one final question left. We only have one obvious question here. So the question is, why do we have to go through all of this complexity? Why do we have to go through all this complexity? Why can't we just count the number of defective wrenches from machine 2 and then count the number of total wrenches that came from machine 2 and divide one by the other and get that same result? Why can't we just do that? Why don't we have that input of the total number of wrenches that came from machine 2 right away? So that's the question. If the items are labeled, why couldn't we just count the number of defective wrenches that came from machine 2 and divide by the total number that came from machine 2? So if you think about it, that's exactly what we are doing. So we're dividing the total number of So this is the total number of wrenches that came from machine 2. At the top, if you multiply it by the 1000, at the top we've got the number of machine 2, so defective, the probability of a part coming from machine 2 if it's given that it's defective times the probability of it being defective. So at the top, as you remember, we got that 5, so the top is actually the number of defective parts that came from machine 2. At the end of the day, we're actually doing that exact thing. The question is, why couldn't we do it right away? Why couldn't the workers just go and count the number of defective parts that came from machine 2 and divide it by the number of parts the overall number of parts that came from machine 2? Why not save some time? Well, the answer to that question can be multifold. First of all, it might be very time consuming. Like in this example, it might be time consuming to calculate the number of wrenches that just came from machine 2. For instance, we might know it might be like a standard metric that the factory measures how many wrenches produced overall, right? So we know that number 1000 or maybe 100,000. But to count them from machine 2, it might take them some time to sit and count through those wrenches, and therefore it's just faster to use Bayes' theorem. The other thing here is that sometimes you might not have access to that information. Sometimes the problem might be such that you just cannot perform that, and you have some inputs like we had in this case, and that's it. And it's not as simple as in this example, and therefore you just don't have access to that information. So there are numerous reasons why you could be in a situation where you can't just go through the straightforward, easy, obvious way, and you need to use Bayes' theorem. So therefore, it's a useful thing to have in your data science arsenal. And moreover, now that we know Bayes' theorem, we can proceed to the naive Bayes classifiers. And to finish off today's tutorial, I've got a quick exercise for you. Perform the same calculation or similar calculations for this value that we want to calculate. What is the probability of a part being defective given that it came from machine 1? So there you go. It's a handy quick exercise just to solidify this knowledge, and I look forward to seeing you in the next tutorial. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is Kirill Eremenko, and in today's tutorial we're talking about the naive Bayes classifier. This is a very interesting machine learning algorithm, and today we're going to get to know it on a very intuitive level. And in line with the super data science mission, which is making the complex simple, we're going to break down this complex topic into simple steps and bite-sized pieces of information. I've got some very exciting slides prepared ahead, so let's dive straight into it. Alright, so here we've got the Bayes theorem, and this is something we talked about in the previous tutorial, so by now we should be quite comfortable with the concept. How are we going to apply it to create a machine learning algorithm? Well, let's have a look. Here we've got a dataset. So it has two features. It has x1 and x2, and there are two categories. Category 1, which is red, and category 2, which is green. But instead of working with these abstract terms, we're going to convert them into something that we can understand a bit better, something that's a bit easier to operate with or to talk about. So we're going to call the y variable, x2 variable salary, and the x1 variable is going to be age. So basically we're representing observations or people that are part of our dataset in terms of their age and salary. As you can see, we have 30 people here on this chart. And the categories, we're going to replace them with walks, meaning that person walks to work, and green will be drives. That means that person drives to work. And so now we get to our problem, to the machine learning challenge that we're going to be solving. What happens if we add a new observation, a new data point into this set? How do we classify this new data point? So as you can tell, this is a supervised machine learning algorithm because we're classifying something based on previously known classes. And so the question is this person going to be classified as a person who walks to work, or is this person going to be classified as a person who drives to work? And the naive Bayes algorithm is going to help us solve this challenge. All right, so how are we going to approach this? We need a plan of attack. It is going to be quite a complex approach, but at the same time, we're going to break it down into steps and it'll all make sense. It'll be very easy to understand. So our plan of attack. We're going to take the Bayes theorem and we're going to apply it twice. First time, we're going to apply it to find out what is the probability that this person walks given his features. And X over here is the features, or represents the features of that data point. So let's go back to the visualization here. So here you can see that this is our new data point. That person has a certain age. So let's say the age of that person maybe is like 25 years old. And then they have a salary. So let's say their salary is $30,000 per year. So those are features of this observation. Right now we're only working with two variables, just for simplicity's sake, so we can visualize things, age and salary. But in reality, there could be many more features. There could be features on how many, what industry they work in, or how many years of education they have, or how long they've had a driver's license for, and things like that, of how far away they live from work. So there could be lots of variables, but at the same time, right now, we're only going to be dealing with two, age and salary. And regardless of how many variables you have, they will be called, and we're going to call them features. So given the features of X, so given the age of 25 and the salary of $30,000, and we'll talk in more detail about exactly what we mean by features just in a moment. And so therefore this part represents that person that we're trying to classify. What is the likelihood of a person with those features X? So we know that we're taking somebody for those features that we have in our new data point. What is the likelihood of them walking? And then we've got the right side. So we're going to talk through each one of these as we calculate them, but for now let's just give them their names going from right to left. So this one over here is called the prior probability, and we're going to calculate that first because it's the easiest to calculate. Next one is the marginal likelihood, and we're going to calculate that second. The third one is likelihood. That's just the names that they have, and we're going to calculate that third. And finally, what we're looking for is called the posterior probability. We're going to calculate that fourth. All right, so that's our plan of attack for step one. This is all still step one, to calculate the probability that somebody walks given those features X that we see in our new data point. Next, we're going to have step two, where we're going to calculate the probability that somebody drives given those features X that we see in our new data point. And again, here we'll have the prior probability, which we'll calculate first, then the marginal likelihood, then the likelihood, and then we'll get to posterior probability. And finally, we're going to compare the probability that somebody walks given features X versus the probability that somebody drives given features X. And then from there, we'll decide which class to put that new data point in. So as you can see, the naive Bayes classifier is a probabilistic type of classifier because we're first calculating the probabilities, and then based on probabilities, we're assigning a class. Alright, so are you ready to perform these steps? It's going to be lots of fun. We're going to take it nice and easy, nice and slowly, so that we understand everything. And after this, you're going to be very comfortable with the naive Bayes classifier. Step one. Alright, so here we have our visualization. Let's move it all to the left a little bit so we can make some space. Now we're going to calculate the first probability in our Bayes theorem. We're going to calculate the probability that somebody walks, right? Just the overall probability. And what does that mean? That is the probability that somebody walks without knowing anything about them. So we're just saying we're going to add a new observation to our data set into here, but we don't know their age and we don't know their salary. We're just going to put it somewhere into our data set. What is the probability that this person that we're adding to our database walks to work? Well, it's very easy and straightforward. From here, we don't have much choice. The only thing that we can do is calculate the number of red observations, the number of people that actually walk, and divide by the overall number. So probability that a person walks to work without any other knowledge is the number of walkers, number of people that walk, which is these red dots, divided by the total number of observations, the green dots. So the gray dot isn't participating in these calculations. So here we have probability if somebody walks is 10 red dots divided by 30 dots overall. Alright, so that was easy. We've calculated the prior probability. Next, we're calculating the marginal likelihood. And this is where things get interesting. So, how do we calculate the marginal likelihood? Let's have a look. Here's our dataset again. And the first thing that you're going to do is we're going to select a radius and we're going to draw a circle around our observation, like that. Now, this radius, you need to select on your own. You need to decide for your algorithm. This is going to be like an input parameter into your algorithm. You can select it less, you can select it more. It's up to you. Now, what does this radius do? Well, what we're going to do is we're going to, first of all, just to make things easier, we're going to remove our dot for now, just so that it's not confusing us. And then we're going to look at all the points that are inside this radius. And what we're saying here is that all of the points inside the circle we're going to deem them to be similar in terms of features to the point that we had. The point that we had, remember, it had an age of, for example, 25 and a salary of $30,000 per year. So now we're going to draw a radius around it, and let's say anybody between the ages of 20 and 30, and in the salaries of $25,000 to $35,000, anybody that falls in that circle. Again, it's not a square, it's not just a square, it's a circle. Anybody who falls somewhere somewhere in that vicinity is going to be deemed similar to the new data point that we're adding to our data set. So as you can imagine, this radius is actually going to have a big say in the way your algorithm works. Well, let's say we have this radius, and this is how it all played out. We have 3 red dots, 1 green dot in there. All right, so now what do we do? How do we calculate the probability of x? And what is the probability of x? Well, the probability of x is the probability of a new point that we add to our data set being similar in features to the point that we actually are adding to our data set. So basically, it's the probability of that new point that we're adding, or like any random point that we add, it's the probability of that any random point to fall into this circle. And P of x is calculated as the number of similar observations, so the number of observations that already we can see in this circle, so 1, 2, 3, 4, divided by the total number of observations, which is 30. So P of x is 4 divided by 30. Once again, just to reiterate, P of x tells us what is the likelihood of any new random variable that we add to this data set falling inside this circle. And it is 4 over 30 because we only have 4. Based on prior knowledge, we can tell that there's 4 here and there's 30 total, so it's 4 over 30. Alright, so that wasn't hard at all as well. We calculated the marginal likelihood. So far we've got this one and we've got this one. Next, we're moving on to the likelihood, and this is probably the most complex one. What is the likelihood that somebody who walks exhibits features X? Well, actually, after we've spoken about the marginal likelihood, calculating the likelihood won't be as complex. So let's have a look. So there's our chart, and now what we're going to do is we're going to draw the same circle again. And once again, we're going to remove the gray point for now, and we're going to color our circle. And so anything that falls inside the circle is deemed to be similar to the point that we're adding. So the question is, what is the probability that a randomly selected data point from our data set will be similar to the data point that we're adding? So basically, what is the likelihood that a randomly selected data point will be from this circle, given, this vertical pipe means given, that that person walks, that we know that that person walks to work. The other way to think about this is we're only working with people who walk to work. So we're only working with the red dots, which represent people who walk to work. So let's forget about the green dots. Now they're faint and we're not even talking about them at all. We're only talking about the red dots. So the question is, given that we're only working with the red dots, what is the likelihood that a randomly selected data point from our data set, from the red dots, is somebody who exhibits features similar to the point that we are adding to our data set? So basically, what is the likelihood that a randomly selected red dot falls into this gray area, into this circle? That's what the question we're asking. And that's also very simple. Now that we know how all of this works, it's basically the number of similar observations among those who work. So the number of red dots that actually fall inside this red circle, in this gray circle, that's 3, divided by the total number of walkers. So total number of people who walk to work, and that is 3 over 10. There we go. So that's our P of the likelihood of somebody exhibiting the feature similar to the data point that we're about to add, given that we're only selecting among the red dots. So that's 3 over 10, and that was our likelihood. So now if we plug all that in, so there we go, that likelihood is done. So if we plug all of that in, we'll get our posterior probability. So 3 over 10 times 10 over 30 and divided by 4 over 30. So if we calculate that, it'll give us 0.75. 75% is the probability that somebody that we put into the place where we're putting X should be classified as a person who walks to work. That was step 1. It was pretty intense, right? Pretty exciting to calculate this value. Now, the next step is step 2. That's step 1 done. Next step is step 2, to do the same thing for the likelihood that somebody with features X will be classified or should be classified as a person who drives to work. And here I'm going to throw you a challenge. I'm going to challenge you to pause this video or rewind back to find out, to have the image in front of you, and do these calculations yourself, to actually go through the same steps and perform those calculations. If you'd like to see and compare to my calculations, then I'm going to put in another video after this one, so another tutorial after this one in the course, so you can just go to the next tutorial and compare. Otherwise, I'm just going to show you the result now. So the result is 1 over 20 for likelihood, or let's start from the right. Prior probability is 20 over 30. Marginal likelihood remains unchanged, 4 over 30. Likelihood changes to 1 over 20. So the probability of somebody who exhibits features X being a person who drives to work is 25%. So that was step 2. Now we're going to do step 3. We're going to compare the probability of somebody with features X, probability of them being a person who walks to work versus the probability of somebody who features X being a person who drives to work. So it's 75% versus 25%, and therefore the first is greater than the second, and therefore it is more likely that that person with features X is going to be a person who walks to work than a person who drives to work. So still a 25% chance that that is a person who drives to work, but percent chance that it is a person who walks to work is greater, 75%. And therefore we're going to classify this point as a person who walks to work. There we go. That is how the naive Bayes algorithm in machine learning works. I hope you found this tutorial useful. I'm pretty excited and pretty proud of these slides, and hopefully this is a step-by-step and simple explanation of a complex concept. And I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. In today's tutorial, I'm going to show you my solution of the challenge that I threw at you last time. So in the previous tutorial, we had the challenge to calculate the posterior probability of somebody being a person that drives to work, given that they are placed in the position where we are placing the new observation for our dataset. So basically, what is the likelihood of that new observation representing a person who drives to work? And the way we need to calculate it is using the Bayes theorem, which is right in front of us. And so now we're going to walk through it. First, we're going to calculate the prior probability, then we're going to calculate the marginal likelihood, and then we're going to calculate the likelihood. And you can compare along the way if you got the same result. So let's go through it. So there's our data set, and now let's move it to the left to make some space. And the first thing we're going to calculate is the prior probability. The prior probability, there's kind of two ways to think about it. So the first way to think about it is if I just randomly select a person from our data set right now, so not including the gray dot, not including the new data point. If I randomly select a person from there, what is the likelihood of them being a person who drives to work, right? So that'll be just the answer to that is the number of green dots over the total number of dots. The other way to think about it is if I just randomly throw a new data point into our data set, right? Just randomly. And without knowing anything about their age or salary, then just knowing all this prior information that we have, the green dots and the red dots, what is the likelihood of that person that we're adding? What is their likelihood to be a person who drives to work? Again, it's very simple because we don't have any other choice but to calculate the probability and assign the probability just based on what we know, and that is just to take the green dots, so the 20 green dots, divide by the total number of dots here and assign that as a probability. So we don't have any other choice, and therefore that's what it's calculated as. So the probability of somebody being a person who drives to work, or a random dot selected out of our existing dots being a person who drives to work, is the number of drivers, which is 20, divided by total observation, which is 30. So there we go, 20 over 30. So that was the prior probability, we've done that. Next one is the marginal likelihood. So let's go ahead and calculate that. And you'll find that the marginal likelihood is actually going to be exactly the same as in the previous tutorial, and we'll talk about this separately. So again, we're going to draw the circle around our observation. We're going to remove observation so it's not in the way. Then we're going to shade in this area. And so now the marginal likelihood is the question, what is the likelihood of, if I just pick a random dot from our data set, just randomly, what is the likelihood that I'm going to pick one out of here? So the reason why we put X here is because what is the likelihood of me picking a observation that exhibits features similar to the features of that point that we are adding to our dataset. So the point we're adding to our dataset, we've just removed it, it's over there. And we've agreed that any dot inside the circle is deemed to be similar to that dot, or in other words, deemed to be exhibiting similar features, so similar age and similar salary to that dot. and therefore that's what we're calculating. So P of X is very simple. We just need to calculate the number of similar observations, the number of observations that actually fall in here, which is 4, divide by the total number of observations, which is 30. So that will give us the likelihood of a new dot falling in here, or the likelihood of, if we just pick out a random dot from our data set right now, then the likelihood of it being one of these is 4 over 30. There we go, 4 over 30. Alright, so that is our marginal likelihood done. And now we're going to move on just the likelihood, and this time is going to be the likelihood of somebody exhibiting the features of X or being similar to the data point that we're adding, given that we're only looking at people who are driving to work. So let's have a look at that. Here's our data set, and again we're going to draw the circle around our data point, take it out, and then add that shading. So now the question is, given that we're only dealing with people who drive to work, what is the likelihood that if we pick one of them, that person will be exhibiting features similar to X? So because we're only dealing with the people who drive to work, we can forget about the red dots. There you go, they're shaded, they're faded out, and now we're only dealing with the green dots. So the question is, given that we're selecting a random point out of all of the people that drive, so this vertical bar drives means given that a person drives to work, so we're selecting a random point out of these, what is the likelihood that they will exhibit features similar to X, which we agreed is the same as they fall inside this circle. And the likelihood of that is 1 over the total number of green dots. So there we go. P of X, given that they drive to work, is the number of similar observations among those who walk. So inside here is 1. Similar meaning similar to our new point that we're adding. And then divided by the total number of walkers. And that's 20. So 1 over 20, that is our likelihood. There we go. So now we can plug these into the formula, calculate the posterior probability. So it's going to be 1 over 20 times 20 over 30 divided by 4 over 30, and it's 0.25, so 25%. So there we go. That was step 2 of our naive Bayes algorithm, or naive Bayes classifier. Hopefully you were able to follow along, and also that I hope that you had a chance to perform that exercise on your own and you got a similar result. And that's it for today. I look forward to seeing you next time, and until then, enjoy machine learning. Hello and welcome back to the course on machine learning. Today we're going to cover off some additional comments about the naive Bayes classifier. Alright, so let's have a look. Today we're going to talk about 3 things. Number 1 is the question, why is it called naive? Number 2 is the P of X and how we can potentially drop it sometimes. I'll show you a quick shortcut. And number 3 is what happens when there's more than 2 features involved in your dataset. Alright, so let's get started. Question, why is this algorithm called the naive Bayes algorithm? Well, the answer is pretty simple. The answer is because the Bayes theorem requires some independence assumptions, and the Bayes theorem is the foundation of the naive Bayes machine learning algorithm, and therefore the naive Bayes machine learning algorithm also relies on these assumptions, which are oftentimes not correct. And therefore it's kind of naive to assume that they're going to be correct. That's the reason why it's called. Let's go back to our example and see what that means. So here we've got age and salary, right? And based on those, we're using the naive Bayes algorithm to classify our data points into people who drive to work or people who walk to work. Well, the Bayes theorem, the way we apply it, actually requires that age and salary have to be independent, or the variables that we're working with, in this case age and salary, have to be independent. And that is like a fundamental assumption of the Bayes theorem, and then you can only apply it, and then you can get those probabilities and so on. But in our case, if you just think about it fundamentally, it is probably not the case, right? Probably there is some sort of correlation between age and salary, because as a person gets older, their experience grows, their number of years that they've spent in the workforce grows, and therefore their salary grows. So it's natural for the salary to grow with age. It might not be a super strong correlation, it's not for everybody, but overall there is some sort of correlation. So they're not absolutely independent variables, and moreover you can even see that from the chart. You can just by looking at our chart see that there's some sort of correlation between the 2 variables. And therefore, given that they are not independent, you can't really apply the Bayes theorem, and therefore you can't apply the Bayes algorithm to machine learning. And that's why it's called naive Bayes algorithm, because oftentimes it's applied even though the variables or the features are not independent or not completely independent, and it's still applied and it still gives good results. And that's why it's called naive, because it's a naive assumption. All right, number 2, P of X. So let's have a look at what we performed. So kind of like rewind and analyze what we did in our steps in the previous tutorial. So in step 2, what we did is we took P of X. So when we were calculating P of X, we drew a circle around our new data point. We removed the data point just so it's not in the way, and then we shaded the area. And so what is P of X? Well, P of X is the likelihood that a randomly selected point from this data set will exhibit the features similar to the data point that we're about to add. And as we agreed, anything in that circle is deemed to be similar to our data point. Another way to think about it is, what happens if I throw in a random variable or random data point into this data set right now? What is the likelihood that it will fall into the circle? What is the likelihood that it will exhibit features similar to the features of the point that I'm about to add into the data set? So basically it falls into that circle. And so P of X is the number of similar observations, or similar observations means observations similar to the point that we're about to add, divided by the total number of observations, which is 30 in our case. So it's 4. We can see that there's 4 points in this circle right now, divided by 30. And the interesting thing here is that this result is the same both times. So this is in step 2. In step 1, where we were calculating for the people who walk to work, so the probability for people who walk to work, it was the same. So basically P of X doesn't change whether you're calculating it in step 1, where we were calculating the probability that the person with these features is a person who walks to work, or if you're calculating in the step 2 scenario, where you're calculating if that person with these features is a person who drives to work. And therefore it's the same both times. So what does that mean? Well, let's have a look at the formulas. So you can see that the formula in step 1, it was P of the probability of a person who exhibits features X, that he or she walks to work, and that was the formula, and you can see P of X is at the bottom. And for step 2, it was a probability of a person who exhibits features X being a person who drives to work, and as you can see, P of X is at the bottom here. So what did we do in step 3, right? So let's move on to step 3 from here. Step 3, we compared the two. So now if we take these two formulas, these right sides of the formulas, and put them into the comparison like that, you will see that at the bottom the denominator is the same. Now that we know that the denominator is not 0 and it's actually greater than 0, probability is never less than 0, and we know it's not 0, so we can just get rid of it, right? So we can multiply both sides by P of X, and therefore the sign won't change, and also we'll get rid of the denominator, and that way we won't actually have to perform that calculation. So that's one less calculation to perform, so you can just compare the top parts of these calculations. And so that is what is done a lot of the time. So if you've done other courses on machine learning, or if you've read some maybe articles on machine learning, you will find that this is oftentimes the case. And also sometimes it is not mentioned that this is happening. So sometimes it's assumed that, or it can be assumed that you know what's going on. So just be careful of that, look out for that. And it's a valid approach, as we discussed. It's totally valid to do it that way, but that is only if you're comparing the two, right? If you're only comparing the two, then you can do that. If you actually want to calculate the value, so we said 75%, 25%, if you want to calculate the value, you can't do that because it'll be too different to reality. It's because you're supposed to divide by a certain value. It's not the actual value. And moreover, if you want to, like, comparing is okay, but calculating the actual value and maybe performing some operations, or you calculate the value from this, you want to compare the value from this scenario to a value from another problem, right? Like a value from a different kind of a scenario where P of X will be different, right? Not from this particular example that you're working with, you want to compare the probability of the person being a person who walks to work in this example to the probability of that person being a person who walks to work from a different example, right, where P of X will be different. If you want to compare across like that, that will also not work because your P of X is different. So be careful of that. It's always the safer way is always just to perform the full calculation. But if you're doing it often, or if you just want to save some time, or if you just maybe reading other literature, then it's also good to know about this approach where the denominator can be dropped when just comparing between the two. All right, so that was another point, or like kind of hint there, or maybe even a shortcut. And so the last point for today, what happens when we have more than 2 classes? So as you remember, in this scenario, we only had 2 classes, the red and the green, or the people who walk to work and the people who drive to work. What happens when we have more classes? How is the challenge different? Well, when we have only 2 classes, we compared, as you remember, we compared the probability that a person who exhibits features X walks to work. So basically that new data point that we added, what is the probability that it's a person who walks to work versus what's the probability that that new data point is a person who drives to work. And it turned out that we were comparing 75% versus 25%, and 75% was greater than 25%, and therefore the probability of that person being a person who walks to work was greater than that person being a person who drives to work, and therefore we decided to classify them as a person who walks to work. And it's very straightforward, and moreover you'll find that every time when you just have 2 classes, it'll always add up to 1. So we didn't even have to calculate the second one. We could have just stopped at this one, because if this is 75%, this one is automatically 25%. It's always going to be like that if you have 2 classes. The way it changes if you have 3 classes it gets more interesting, right? So you've calculated 1, and then there's still 2 more left. So if you're working with just 2 classes, as soon as you calculate 1, you're done. You can decide right away. If it's greater than 50%, then you assign that class. If it's less than 50%, you assign another class. If it's equal to 50%, then you've got like a tie. Whereas if you have 2 or 3 or more classes, then just calculating the 1 won't be enough, because then you have 2 other ones and you would still have to calculate at least another one. So it just means that it's more of an interesting selection problem when you have more classes. That's pretty much the main thing that changes when you have more classes. And there we go. That's all for today. I hope you enjoyed these extra tips on the naive Bayes classifier, and I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click extract here. If you get this macOS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the macOS folder and you can get rid of the zip folder now. And also with the k-nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. Today we're going to implement the naive Bayes model on Python. So let's start right now and let's find out about the results. So we're going to go to File Explorer here to set our folder as working directory. So we'll go to Machine Learning AZ folder, Part 3 Classification, Naive Bayes section, and here we are. Make sure that you have the social network add CSV file, and if that's the case, click on this button to set this folder as working directory. Now we're going to take our classification template to be efficient and get the final result even quicker. So we'll copy this and paste all this here. And now what we only need to do is change a few things. First we need to create our classifier here, then we need to change the name of the classifier here, so it's here naive Bayes, and same as here naive Bayes. So yes, I'm doing that right now so that we don't forget. And now we are ready to change the last thing, which is to create our classifier. And you're going to see how it's going to be so simple. We will just need to write 3 lines, well, as usual, as for all the classifiers we made so far, but you will see we won't have any parameters to include. I'll show you. So remove this, and then let's import the class for the job. So the class for this job is the Gaussian NB that we want to import as a class. So let's do this. It's actually from the scikit-learn naive Bayes library. So we're going to write here from sklearn.naive Bayes import Gaussian NB. And that's it. That's the class that we're importing from this library. Alright? And now let's create our object. So our object is, well, we call our object the classifier equals, and then of course we're going to call the class here Gaussian NB. Now if we press Command I to inspect the Gaussian NB class, look at what the arguments are. Well, actually there is no argument. So that's why it's so simple. Here, as you can see, we have an example and we only need to call the class. We don't have any parameters to input, so that's kind of cool. We don't have anything to do here. And so now let's fit our naive Bayes classifier object to our training set. So to do this, as usual, we start by taking our classifier object and then use the fit method to fit the naive Bayes classifier to our training set. So xtrain here and ytrain as usual, nothing changes. So now it's ready. We are ready to execute the different sections of this code. So let's do this. We're going to start by executing all the pre-processing steps. So it's from here to the top. Alright, and now Command or Control plus Enter to execute. And perfect, all executed properly. You can check in Variable Explorer that we have all the right sets created. So we have our data set here, our training set with xtrain and ytrain, our test set with xtest and ytest, and so everything looks great. We can even check that xtrain is scaled properly. Yes, we can see that it is scaled very properly. So here is the age column and here is the estimated salary. Okay, and now let's select this to create our classifier. So Command and Control plus Enter to execute, and our classifier is now created. So perfect, as you can see, remember for the other classifiers, we had all the parameters selected by default. Well, here, since there is no parameter, there is just this Gaussian NB here in the output. So everything looks great, everything is easy. Awesome. Now let's select this to get our vector predictions. Here we go, white bread created. Let's look at white bread. And let's open as well white test so that we can compare the two. It looks great so far. We can see that the 6 first predictions are correct predictions because here are the true results, the true observations. The user didn't buy the SUV in reality. And here the 0 are the 0 predictions. That is, our classifier predicted that this user didn't buy the SUV. So that's correct predictions. Same for the 7th user. The 7th user bought the SUV in reality and the prediction says the same. Okay, so the 8th is correct, however the 9th is not correct because in reality the user didn't buy the SUV, but our classifier predicted that this particular user bought the SUV. Okay, so as usual, that's not the best way of looking the incorrect predictions. The best way is to take our confusion matrix and have a look inside. So that's what we're doing right now. We're selecting this code section here, generating the confusion matrix. Here we go, confusion matrix created. Let's have a look. And in the flashlight we can see the number of incorrect predictions. 7 plus 3 equals 10 incorrect predictions out of 100 incorrect predictions. So not too bad, but we can do better and we will do better. So let's press OK, and now let's get straight into the most fun part, which is the visualization of all the results. So let's select all this and press Command and Control plus Enter to execute. And here we go. Wow, that's actually a beautiful curve. That's what I was telling you. I was telling you before that, we had this straight line for the logistic regression, and then we had this KNN prediction boundary that contained a lot of irregularities that made it not that beautiful. But here we have a beautiful curve that actually let's enlarge this to look at the result. So yeah, I was saying here we have a beautiful curve, a very smooth curve with no irregularities. Well, that's proper to the naive-Bayes model. That's because of the way naive-Bayes model work. So not only it's a beautiful curve, but also it manages quite well to catch these older users with a low estimated salary who actually bought the SUV, which the logistic regression and the SVM couldn't classify correctly because there were linear classifier and therefore the separator, the prediction boundary was a straight line. But here it's making a curve, so it manages to catch most of them. We still have some of them who are the most rebellious and who managed to beat the naive-Bayes classifier, but anyway, it made a pretty good job here. Now a good exercise for you is to try to understand how the naive-Bayes model managed to classify all our data points which are nonlinear separable in this red region and this green region. And that's based on what you learned with Kirill in the intuition tutorials. Try to understand how naive-Bayes did that by applying the theory that you learned with Kirill to this particular set of data points and this particular problem. That's a very good exercise that will shape your intuition of naive-Bayes even in a better way, and you will become even more machine learning experts. Okay, so that's the training set results. So let's have a quick look at the test set results. The test set results are right here, so let's have a look. Let's select this from here and press Command and Control plus Enter to execute. And not bad at all, not bad as well. Let's look at that. Alright, so that's the test set results. We can see that most of the red users, that is the users who didn't buy the SUV, were predicted correctly by the naive-Bayes classifier because they ended up in the red region, and same as the green users who are the users who bought the SUV and were predicted correctly because they fell into the green region. Of course, we have some incorrect predictions, and if you want, you can count the number of incorrect predictions, that is the number of red points in the green region and the number of green points in the red region, and you will find the number of incorrect predictions we found in the confusion matrix, which was 10 incorrect predictions. Okay, so do this exercise, try to understand how naive-Bayes obtained such a result. So, that's the exercise of combining the theory and the practice by understanding how the theory works onto this particular practical problem. Thank you very much for watching this tutorial. I hope you like this new curve. This is kind of a new result we're obtaining here. And we are not done with the surprises, because you're going to see that we will obtain some more different shapes of the contour, that is of the prediction boundary here. You're going to see it will be with decision trees and random forests, and I can't wait to show you this. Until then, enjoy machine learning! Hello and welcome to this R tutorial. Today we're going to implement the naive Bayes algorithm on R. So let's start right now. Let's first set the folder as working directory. So I'm going to part 3 classification, and that's the folder. So make sure you have the social network add CSV file, and if that's the case, click on this more button here to set this folder as working directory. And now let's start implementing naive Bayes on R. So we're going to take our classification template, we're going to take everything from here to here, and then paste right here. And now we just need to change a few things. So first, let's change the titles, our usual, so that we don't forget. So here we are with the naive Bayes classifier. Same for the training set. So that is plotting the title in our graphs. And now what we'll need to do is to create our naive Bayes classifier. So let's do this. I'm going to remove this. And now what are we going to do? Well, it's actually funny because we're going to use a library that we already used before, but for a different classifier. It's the E1071 library. So there is no surprise why this library is very popular, one of the most popular ones, because it contains a lot of tools for SVM and tools for naive Bayes. So here again we'll use this library. So for those of you who didn't follow the SVM tutorials on R, and for those of you who are starting R for the first time, maybe you don't have the E1071 packages in your packages list. So if that's the case, you just need to type the command here install.packages, and then in quotes here in the parentheses you just add the name of the library, which is E1071, and then you just need to select this and execute to install the package. I won't do it here because I already have mine installed, but I promise you it will work properly. So I'm just going to put that in the comment. Here we go. And now let's just also import the library that is to select it in the packages list, because here it's selected, but it might not always be the case. And if you want to automate your machine learning scripts, it's better to always have this script line here that selects automatically your packages. So library E1071, and now we are ready to start creating our naive Bayes classifier. Okay, so let's do this. As usual, we will create a variable classifier, and then we will use the naive Bayes function of the E1071 library. The E1071 library contains a lot of functions, and one of them is to create a naive Bayes classifier. Okay, so careful with the capitals. So it's not capital N but capital B. All right, but then you know R is helping you with the terms, so you would have this naive Bayes popping up here, so you just have to press enter. And now let's input the parameters. So the parameters, what are they? Let's look at them. We press F1 here to have a look, and here they are. So we will actually need to input only the 2 first arguments. We won't need to input the formula like for the other one. It will work perfectly well with only the first 2 ones. So you'll see, let's input X here, which is, by the way, the training set. So the training set, but we need to remove the last column of our training set because X is actually the matrix of features. You see, it's written here a numeric matrix or a data frame, and by that they mean the matrix of features, that is the matrix of the independent variables. So here, since the training set contains both the independent variables and the dependent variable, we need to exclude the dependent variable. So to do this, we're going to add brackets here and remove the last column by inputting here a minus, and then the index of the last column, which is, well, we can see here it's -3. So it's -3. All right, so perfect. And then comma, and then next argument. So do you guess what the next argument is? Well, of course, to train a classifier, we need the independent variables and the response. And the response is the dependent variable. So, of course, y is going to be the dependent variable. So, y equals, and to take it, we're going to take it this way. We're going to input training set dollar purchased. So I'm choosing to write it this way because we can clearly see that we are taking the dependent variable purchased. Alright, and that's all. You will see that it will work perfectly well. So I'll show you right now. Let's select the, so before we have to select what's above, which is all the pre-processing steps. So Command and Control plus Enter to execute. Alright, pre-processing well done. We're good to go. And now we can create our classifier. So yes, let's do this. If your E1071 package is not selected, you need to select that as well. So Command and Control plus Enter to execute. And here is our classifier. Awesome. So as you can see, it works perfectly well. The classifier is well created using only those two informations. And when you think about it, well, this is all we need to train a classifier, because we need the information of the independent variables and the information of the dependent variable, so that it can learn the correlations between the independent variables and the dependent variable. Alright, so that makes sense. And now we can create our vector of prediction ypred using the predict function on our classifier and on our new data, which is the test set. So here we go, ypred is created. Let's have a quick look. Ypred. So for the first time, we're obtaining something here. Remember before, when we entered ypred in the console, we had all the predictions listed in the console, but here we have this factor 0 here. So that means that ypred is a vector of factors, but with no factor. So it's basically an empty vector. And that is because the naive Bayes function of the E1071 library didn't recognize our dependent variable vector purchased as a categorical variable with 0 and 1 factors. So far, the libraries and functions we've been using recognized the dependent variable as factors, so we didn't have any issues with our predictions, and we didn't have to encode the dependent variable purchased as factors. But here with naive Bayes, it's not the case. It doesn't recognize the dependent variable purchased as factors, so we need to encode it as factors. Because, as you can see, if we try to compute the confusion matrix below, we will get this following error message: all arguments must have the same length. Well, yes, indeed, we have a problem, because the two arguments here are test set 3, that is the third column purchased of the test set, and then ypred. So since test set 3 has length 100 and ypred has length 0, because it's an empty vector with no factors, then obviously we cannot compute any confusion matrix. So what we need to do is to jump back up to the preprocessing first step to encode our dependent variable purchased as factors. Then the naive Bayes function will recognize the dependent variable as factors and will perfectly be able to create a classifier that will allow the predict function to return the expected vector of predictions ypred. So it's great that you see this error, because this is a classic error in machine learning in R, and that way from now on you won't make this error in the future, or if you make it, you'll know how to fix it. So let's do it right now. Let's add a new code section here, and let's call it encoding the target feature as factor. Alright, and now let's factorize our column purchased. Okay, let's do this. So we will take it from start. That means that we will take the purchased dependent variable column of the dataset, and then we will recompute all of these to set this purchased column everywhere for all our sets. That is a training set and the test set. Okay, so we're going to take our last column from our dataset. So we're going to type dataset $purchased, right, equals factor, and in parentheses dataset, and then again we're taking the purchased column, that is the dependent variable column of our dataset. So again we're taking the $sign here in purchased to take this column, and then here we will just specify the levels. So our levels are C, 0 and 1, alright, And that's it. That's how you encode your dependent variable column purchased into factors. And that's actually what we saw in part 1 data preprocessing when I explained how to encode a categorical variable and set it as factors. Well, here we have to do it. And actually, we are going to leave that in a template. We're going to leave this encoding the target feature as factor, because even if we encode the dependent variable column for our other classifiers like logistic regression, SVM, and the other classifiers, then it will even be better to have this purchase column encoded as factors so that we can know for sure that R recognizes it as a factor. Okay, for some classifiers we don't need to specify it, but let's include this anyway so that we never get any error. Alright, so we're going to start from scratch now. So to do this, we can clear everything, so that's what we're going to do. Clear everything here, so we're clearing the data. Clearing the script here, so I'm pressing Ctrl L to clear, and that's it. And now let's do the whole thing, and you're going to see that we won't get the error. So let's select this. Okay, so that's all the data preprocessing steps with now the encoding included. So execute. Alright, now we're going to fit the naive Bayes model to the training set. Execute. All good. Now we're going to create our vector of predictions, ypred. Okay, you're going to see that if I type ypred here, we will now have the predictions. So we can compare it to yset, which is the third column of the test set. Okay, so we can compare them, but let's not do this. Let's just get to the point where I want to show you that now a confusion matrix is going to be created without any error. So let's select this, execute, and now, as you can see, the confusion matrix is created without any problem. So, and now we can have a look to see the number of incorrect predictions, which is 7 plus 7 equals 14 incorrect predictions. Not bad out of the 100 observations of the test set. Okay, great. And now we're finally getting to the fun part, which is to visualize the results. So if you didn't follow the Python tutorials, a good exercise for you is to try to predict what's going to happen, predict what you're about to see. Based on the intuitions that Kirill explained to you, can you guess what prediction regions are going to be? And especially the prediction boundary. Can you guess what it's going to be? Is the naive Bayes classifier a linear classifier and then it will be a straight line? Or is the naive Bayes classifier a non-linear classifier, but then is the prediction boundary going to be a smooth curve or a prediction boundary with a lot of irregularities like for K and N? That's a good exercise, you know, to try to practice your intuition that you have just built. You need to practice it now. Okay, so you can pause on the video, and now I'll just select this to show you if your prediction is correct. So let's see, Command and Control plus Enter to execute. And there is our naive Bayes graphic results. Isn't it beautiful how this prediction boundary is a smooth curve, classifying quite well the datasets. That is a dataset of observations non-linear separable. It's kind of like the kernel SVM curve, you know, it's a beautiful smooth curve that manages to catch those green users that couldn't be caught by linear classifiers because we had the straight line, and therefore it couldn't catch the green users here and put them in the green category. They were in the red category. But thanks to this curve, we can see that it's making less incorrect predictions, but still some, like those 1, 2, 3 here, regarding these users here, these older users with a low estimated salary that were incorrectly predicted by the linear classifiers. And then, however, it's still making some few mistakes here. We would have liked to have a lower curve here, like the curve starting from here, but that's what naive Bayes could do here, and that's already quite a good job. So now let's see what it does on the test set results. Here we have the test set results code. Let's execute it. And here's the test set. If the execution of this code is taking too much time, you can try to take a lower resolution, because right now you can see that we have a very high resolution with this by 0.01 step here. We cannot see the pixels here thanks to this resolution. If you take a 0.1 resolution, the script will execute much faster, but then you will see the pixel point, so it's as you want. So the test set results are actually not bad as well, it did a pretty good job classifying those green users here to the right green category, but still some incorrect predictions resist since those green points here stay in the red region. Alright, so that's the naive Bayes graphic results. I hope you enjoyed what you saw. We're gonna have other different surprises of other classifiers. You'll see that we will get very different kind of prediction boundaries when we look at the decision trees classifiers and the random forest classifiers. So I look forward to showing that to you, and until then, enjoy machine learning!